boppity ding ding boo boop de boop de poop. Boo 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 boo.
Okay, your intro music has been captured.
All right. You let me know when it's ready to roll there, buddy.
Yeah, it's rolling. Like,
Okay.
that's what I meant by.
Oh, sorry. Okay, cool. Hey, hey, hey. Welcome to another edition of Tim Starting Off, the Tutor Wizard stream today. I suppose in many ways this is a case of Adrian's following the dog and pony show. So he'll be on around 2-ish. So I'm going to do the first hour today. I want to do some review of statistics material for my statistics people. But the general plan, so this is the general plan today, is we're going to talk stats for a while. Then we're going to have some linear algebra, because I've been pushing Adrian to take a look at some interesting questions that are showing up on practice final exams. So that should be on around 2. And there's always room for calculus questions for anybody who's tuning in. If you've seen our posters around the University of Alberta or MacEwan, we will field whatever questions you have for your upcoming final exams. But this is the general plan today, and as with all people who studied von Clausewitz, very few plans ever survive first contact with the enemy. But of course, I'm not suggesting that you're the enemy or anything. I'm just talking about chaos in the general universe. All right, so I want to get busy and get doing this stuff. Oh, I should also mention that if you missed something today or you want to review it, we do archive our videos online as well, because you know the Tutor Wizard also has the YouTube channel, and we're probably going to be putting stuff up on Patreon as well. We've got a couple of glitches to work out with Patreon, which is why we're doing things a little differently today, because at the end of the day, we're all old and technology is beyond most of us. That's a wink, by the way. I don't have anything in my eye. I'm giving you the nudge, nudge, wink, wink thing. Okay, let's get busy. Now, my thoughts on the upcoming statistics exams, whether it's for 151 or 161, is that, and I'm basing this on a trend over the past few semesters, where they're moving away from a calculation-dominating test to one that tests your knowledge of ideas and concepts. So we're going to start off with that today. We'll probably do a little bit of computation as well. We'll see how the clock ticks here. And I know for 161, some of the topics that I'm going to talk about in 151 aren't going to be tested. At least that's what you've been told. But let's wait and see what actually happens on the exam. So I am going to cover a fair bit of material, and even if it may not be relevant to you precisely now, it certainly will be relevant if you take, well, the follow-on course in the business faculty is Management Science 212, which if you're taking 161 statistics, I'm pretty much sure you're going to be taking Management Science 212. All right, enough of that nonsense. Let's talk about a few things. Now, I think we're going to start with simple linear regression, because this is there's a number of definitions that reside under the topic of simple linear regression that can be tested quite easily on a multiple choice exam. So, for instance, correlation. All right, the definition of correlation. And I will write this down, but I'm not going to expect you to, try to keep up with my handwriting, or who's kidding who. You're going to be able to read my handwriting. So I'll tell you what the definition is. I will put it on the board, but it'll be a combination of verbal and written. Ooh, I almost sound like an instructor. No. The peanut gallery's awfully quiet today. Lorenzo, are you alive over there? Okay, he is. Okay, just checking.
I'm trying to make my computer work.
Yeah, well, Adrian's just on the other side of the camera here, looking for the lost bookmarks file from his laptop. Oh, holy mackerel, he found it. Right on.
If not, I just re-added it.
Oh, you did? Okay, cool. Whoa, I got that old man look going on here. I haven't been sleeping very much lately, and I got the bags going on here. I hate that. Okay, no matter what. Speaking of bags, there he is. Okay. What is the definition of correlation? Well, correlation applies to two variable statistics. Typically, x is your explanatory variable and y is your response variable. It doesn't have to be that way, but that's typically how we do it. And correlation then is the value that measures the strength of association. Whoops. There we go. So this is that handwriting thing I was telling you about. So correlation measures the strength of association between two numerical variables. That's the definition. I'm going to write that down, then we're going to talk a little bit about some of the things that it is and some of the things that it is not. So it measures the strength.
Right?
What's that?
Correlation immediately implies causation.
Correlation does not imply causation. That's true. You tried to catch me on that one, didn't you? Yes, you did. So, yeah. Look, shouldn't you be reviewing a file or something?
I couldn't find any of my bookmarks. I'm crying in the corner.
Okay. Measures the strength of association. Okay.
Yeah, can you go to Mega?
Between two variables.
I hate reading it on.
All right. Now,
Question if you do want to address
what are the details about correlation? Correlation is simply a number that ranges between -1 and +1, with 0 right in the middle. So it's symmetric around 0. Correlation has no units. If someone tells you that the strength of correlation between the weight and time axes is 27.3 kilograms per second, it's clearly wrong because you have units attached to it. There's no units here. Plus the fact that I also used an integer value in there that's quite a bit bigger than 1. Don't take the bait on something like that. Correlation is not a percentage either. Coefficient of determination is. I'm going to come to that here in a moment. So we're going to get to that in a minute. The other thing I want you to understand too, in thinking again towards the exam, is that correlation is bidirectional. So it doesn't matter if I say to you the correlation from the explanatory variable towards the response variable is 0.6. Well, if I change the order around and say the response variable is correlated to the explanatory variable by 0.6, this is a true statement. Don't change the number, don't change the sign. Correlation goes both ways. It is the perfect statistic for the modern world. And I'm waiting for the peanut gallery to comment on that.
What?
Look, you missed my joke. God, get no respect around here. I
You
said
said
correlation.
look up the Math 125 exam, and then you're like, now respond to my jokes. Damn, monkey, I danced all fucking semester. I'm done.
I have a bitter monkey over here in the peanut gallery. He's not getting enough peanuts, apparently. I said peanuts. No, my joke was that correlation being bidirectional is the perfect statistic for the modern world.
Oh, there you go.
How many kinds of sex changes?
This is not working here. I'm trying to do stand-up and do math at the same time, and I'm failing miserably at one of those. Okay, so let's move on here to r squared. So r squared is the coefficient of determination. Coefficient of determination. And it is a percentage. So the definition of r squared is the percent of variability in the response variable, typically y, that's explained by your choice of explanatory variable, typically x. So if r, for instance, was 0.60, then r squared would be 0.36. And we would interpret that as the explanatory variable explains 36% of the variability in the y variable, in the response variable. And that's going to be on the exam. There's going to be a question on there about this. For sure there is. And oftentimes they tangle that up with, well, the typical example that I'm thinking of is they're going to give you some information about the simple linear regression equation For instance, they may say that the slope of the regression equation is negative 5.2, and r squared is 0.25. And it'll ask you what r is. Well, you're going to take the square root of 0.25, and you're going to get 0.50. And on the multiple choice, that'll be one of the answers. And you're going to circle it, and you're going to be wrong. Because the sign on the slope, which I told you was negative, the sign on the slope has to match the sign on r. They have to be the same. But when you take the square root, you only get the positive root back, not the negative root. So because the slope is negative, we say that r, which we rooted to get 0.50, is negative 0.50. Watch out for that. That question shows up all the time, and lots of people get it wrong. So for people who like notes, I'll write it down. So r squared, the coefficient of determination, its definition is the percentage, I'm just going to use the symbol percent, the percentage of variability in the y, or response variable. That is explained, or can be accounted for with, that is explained by your choice of explanatory variable. Because remember, with simple linear regression, and you're studying something, you've made a choice about what the explanatory variable is. And sometimes you don't know if you're making the right choice. So the tool, the usage of this tool then is, how useful is your explanatory model, which is your y hat is equal to b naught plus b1 times x. If it's a useful model for making predictions, r squared will be large. It'll be close to 1. The closer it is to 0, the less variability, the less explanation, the less predictive power your model has. So keep that in mind. It's not so much important in this course, but when you take a second stats course, this becomes an important concept. So let me finish writing this out. So the percentage of variability in y, the response variable, that is explained by x, the explanatory variable. Bazinga, there we go. Okay, so there's two very important concepts from simple linear regression. I'm going to talk about a couple more, and then we're going to move on to a few other topics, all right? I'm just going to check. So if you're wondering what I'm looking at over here, we now have the laptop set up so I can take a look and see how things are lining up here. I just wanted to see if the camera's catching everything well, and it looks like it is. Okay, moving on. Moving on down the road. I got a case of the white line fever. Bazinga, bazinga. White line fever. Country song. Also a TV show from the 70s. Look it up. I feel like nostalgia in the 70s were a good 50-some years ago. Ooh. I'm kind of sad to say that I'm old enough to remember some of that crap. Holy mackerel, we got half a dozen viewers today. So a shout out to some of my students. Hi, Caden. I'm glad to see you online. I'm assuming you're hiding there with us. Also, shout out to Shay and also to Abby. Greetings, if you're here. I'm just looking at some of the other stuff going on here. Is correlation related to causation at least? Oh, that was where that came from. Okay, so this is for Math Pond, asked that question. No, I don't want to even chip away at hinting anything like that. The problem with correlation and causation, it's very hard to prove A caused B, because there's always going to be extraneous variables. If you think about the campaign to control cigarette smoking, this went on for decades. Who's kidding who? It went on for generations. The association to oral and lung cancer was known in the late 1800s, I believe, people who smoked cigars. Sigmund Freud comes to mind. He died of oral cancer. You know, Mr. A cigar is just a cigar. Yeah, well, sometimes it's also your death. Anyway, there's a number of famous people, it's not hard to find them online, who succumbed to tobacco use. But the tobacco industry, particularly in North America, I'm looking at you, United States of America, because that's the dominant culture. It was always easy to counter arguments about smoking causing cancer because there's so many other extraneous variables. And remember, throughout the industrial age, there was plenty of other noxious chemicals in the atmosphere that could equally be attributable to the cause of your cancer. So it took a lot of very carefully controlled experiments and studies to get to the point of irrefutable causation. So is there a relationship? Let's say that there's always going to be some hints. Correlation will point you in a direction to go looking for more evidence, but it's never going to even provide the slimmest of irrefutable evidence. Notice I'm using the word irrefutable, because evidence that is irrefutable is very hard to get. You know, you can spend a lifetime trying to have that happen. So I would say that the best thing to say about correlation is it points you in a direction to go looking for more, better evidence or information to study things with. Okay, moving on, because I got a few things here to cover. Okay, we see that. All right, we're good there. All right, so we should also talk about slope. So B sub 1, also known as beta sub 1, is the slope of the regression equation. And it has a definition that will allow you reasonably simple computations. And I'll do an example of this here in a minute. The slope is going to tell you the expected change in the y variable. So the expected change in your response variable, given a unit change in the explanatory variable. Now, you got to be careful. I said unit, and that's the definition, but units don't have to be 1. I mean, if we're talking about, say, increments in terms of years, sure, a unit will be from from age 2 to age 3 is an increment of 1 unit. But if you're talking about, say, a regression equation that will provide the cost to rent retail space, well, that might be provided in units of 10 square meters. So a unit increase there isn't from 10 to 11, it's from 10 to 20. So now you need to read the question very carefully to know what they've defined as an increase of a unit. And there's 2 ways to do that. The easiest way is to use the definition of the slope. Let me put up an equation here. We're just going to say, well, let's do the price thing. Okay, so I'm going to use $. In other words, the price to rent some retail space is equal to 500 plus 100 times a unit of space. Now, I am defining the unit of space in terms of 10 square meters. So let's say, for instance, we're renting, I'm going to do this 2 ways, so there's a way here for everybody, even if you're not a, who we got on here? Who says hi? Heretic, hi, Heretic. Hope you're doing stats. If you're not, we have linear algebra and calculus coming up, so hang in there. Now, let's talk about this. Let's say you want to rent 200 square meters of retail space. Okay, well that's 20 units of 10. So let's see what that costs. So 200 square meters divided by 10 gives us 20. So that means I'm going to put 10 in here. What am I saying 10 for? I'm going to put in 20. So we have 500 plus 100 times 20. So remember, the 20 represents 20 units of 10 square meters each. So this is now $2,000. So the cost to rent space is $2,500. And I'm going to talk about B sub 0 here, the y-intercept, in context of this question in just a moment. So just hang 10 on that. I'm sensing through the Ethernet that someone's going, what about the y-intercept? Well, we'll get to the y-intercept in a minute. Okay, so now the question may be, how much extra do you expect to pay if you want to increase your retail space rental by 1 unit? The heck was that? Oh, someone's being a smarty pants here. Whing! There we go. So if I'm increasing by, well, let's say I want to go, let's make the question more hard because let's face it, it's an exam. Let's say we want to go from 200 square meters to 260 square meters. Well, the long way would simply to plug in, another 3 units and recalculate. But remember, I'm going up by 60 square meters, and each square meter is in units of 10. So I'm going up by 6 units. So I'm going to increase. So what I'm going to do is I'm going to take the slope, which is $100, times the fact that I'm going up by 6 units. Remember, 60 square meters divided by a unit of 10 square meters where I'm getting the 6 from. So this is another $600. So now I have the answer to the question. My monthly rent will increase by $600 if I go from a rental of 200 square meters to 260 square meters. That's the easy way to use the slope definition to compute the answer to the question. Well, of course, the other way to do this, and both are perfectly valid, and no one's going to give you a hard time whichever way you use it, is to simply recompute at the new value. Okay, so we have 2,500 as the initial, and now I'm going to write 500 plus 100. Now remember, I'm going to 260 square meters, divide out units of 10, so now we're multiplying by 26. Well, that's 2,600 plus another 500, so now we have 3,100. This is the new cost. And then we simply subtract the old cost from the new cost, so 3,100 minus 2,500, and we get the same $600 price increase to rent that space. That's it. You don't have to do it any one way. I don't care how you do it. It's just a matter of doing it. They both work. And the thing is, if you are going to take Stat 252, the follow-on course, or Management Science 212, also the follow-on course, the Faculty of Business, this is pretty much a common question. And it's even more interesting when we start doing this with multiple linear regression. There's some really interesting things that happen in that on how you can take an equation that's got 6 explanatory variables, tinker with it a little bit, and end up with one with 2 explanatory variables. Kind of fun, actually. Okay, so that's the definition of slope. I'm not going to write it down. I think I'd rabbited on about that enough. But I did say I was going to talk about the role played by the y-intercept. So recall, our equation was the price to rent retail space was 500 plus 100 times whatever the units are. Okay. So now I'm not concentrating on the units anymore. Now I'm just looking at this 500. Because this is B sub 0. That's the called the y-intercept on Microsoft Excel. The output will just be labeled as constant. Well, the role played by this mathematically is all that's left of the equation is the y-intercept when the unit value is 0. That doesn't really tell you much. That's just common knowledge that you learned in grade 10 when you were studying y is equal to mx plus b. It's where the line crosses the y-axis. That doesn't really mean anything, right? But in context of a question like renting retail space or other things, this is fixed costs. So what are fixed costs in retail space? Well, there's taxes, maintenance, janitorial services, general upkeep, profit. You know, it's all rolled into fixed costs. And that's how you interpret it. If this was the equation to, say, find the price of a vehicle based on its age, it would be the price of a new car. Because if the car is new, its age is 0, and then all that's left is the base cost of the vehicle. Typically, obviously, the equation is going to have a negative slope on it, so as age increases, the value of the car decreases. You know, that's just another example. So read the question carefully, and you should be able to figure out the answer to that. You know, generally speaking, when it comes to reading questions in this course and trying to find the answers, because regardless of whether it's 151 or 161, the exam's multiple choice, right? And there are 5 choices per question. Well, usually 3 of those choices are absolute nonsense. You'd be foolish to pick any one of those 3. That leaves you with 2 plausible, and certainly one of them will be a much better answer than the other. When it comes to theory, I would say take the one that reads the most like it came out of a textbook, because quite frankly, it probably did. Sometimes in contextual questions like that, the one that gives the best or most detailed explanation is quite often the one you want. The point is you need to bring some smarts into writing these exams that are not strictly related to mathematics, but related to your ability to read critically, which is what makes this course kind of hard, because people go in thinking, oh, it's math, and I'm terrible at math. Yeah, but if you're good at reading, you can get through this course. You know, the algebra is minimal, and the arithmetic is aided by a calculator, so that's always a good thing. How are we doing on the clock here? I don't want to overrun here my time. I have other things I wanted to talk about. No, I've been talking for half an hour yet. We've got a little bit of time. So we got that out of the way. So those are the simple linear regression definitions I wanted to talk about. Now, a question often comes up. I had this one last week from somebody. How do I know when to use the t-test versus a z-test when we're dealing with mean values? Now, let me illustrate this with a couple of formulas. If we're talking about the probability of a single observation, call it y, that's being compared to an expected value, and we divide out the standard deviation, this is our z formula. And of course, to answer the question is going to go to the z table, and you'll get a p-value for, you know, whatever you need to answer the question. But you'll notice that this is a single value. It's not a mean, and this is not standard error. So this is a single y value question, typically related to probability associated with the standard normal distribution. But soon as n is bigger than 1, actually, let's write that. So this is a single y value. In other words, n is 1. And I'm giving you population, standard deviation. Remember, if it's a Greek letter in statistics, Greek letters refer to parameters. They refer to the population. Never something that you measured. The things you measure are usually in the Latin characters, so like y, or p hat actually, if we're going to be fussy about it. Now, what happens when n is not 1? Well, then y becomes y bar, so now you have an average of a sample. Again, we're comparing it to an expected value, mu, but now the standard deviation is replaced with the standard error, and we have sigma, little sigma, divided by square root of the sample size. And that's how the formula changes. Now, here's the thing. The first formula I put up here, z is equal to y minus mu over little sigma, is on the formula sheet. The second one is not on the formula sheet. You need to know it. You need to know how to make the change. The most significant change is the denominator. Now, what happens when we don't know what the population standard deviation is. Well, if we don't know that, then we do know the standard deviation from the sample. And that's when we shift to the t-test and the t-probability distribution. We still have y bar minus mu, but now the denominator is little s, which is sample standard deviation divided by the square root of n. And remember, there's degrees of freedom on this, which is n minus 1. We're not going to talk too much about that today, but what I wanted to point out was a simple mnemonic on how to remember all this. Well, consider the alphabet. Here we have S for sample standard deviation and is used in the t distribution, so the t-tests all use S, sample standard deviation. And when you look at the alphabet, T follows S in the alphabet. These two letters are side by side. So if you have S, you have to use T. It makes sense, okay? If you have sigma, little sigma, not capital sigma, and you're dealing with mean values, then you use the Z distribution, which of course we see that right there. So here's your mnemonic. S and T go together. And for most of what we're doing in this course after the midterm, this is one of the formulas that you're going to use. Okay, I wanted to get that out of the way because that's one of those little things that trip people up. Now, this naturally leads us, well, the commentation, is that a word? Well, it is today, about degrees of freedom and standard errors naturally leads to a discussion about the central limit theorem. It's my cheat sheets down here, my little notes, so I remember what I'm doing. Let's talk about those because the formula sheet has them on there. There are 7 bullet points, but the problem with the formula sheet is they're written in terse mathematical notation, and for the average student in statistics, you might as well not write it down there at all because they're going to go, well, I don't know what the hell that means. So let's get this out of the way. Now, what you're going to see on there quite often is the notation capital N mu comma sigma. This is shorthand for the normal distribution. N for normal distribution. The center is mu, the spread is little sigma. And remember, this gives you all the information you need to draw a bell curve to describe a distribution because the center of a bell curve is going to be signified with mu, and how wide the thing is given by sigma, which is what you need. Remember, in the labs, you were asked to describe the characteristics of a histogram. And they used to leave it just at that, and people would get it wrong all the time because they really wouldn't pick up on what they needed to say. When you describe the distribution, the characteristics of a histogram, you want to know where's the center. You want to know how wide it is. Center and spread. That's what we're doing. We want center and spread. And now they tell you that, so you have even less excuse for not getting it right. Anyway, so my point is, this is the first piece of opaque information for many students. N bracket comma mu, or part bracket mu comma sigma close bracket is shorthand for the normal distribution. In other words, you're going to use the Z table. Now, a word to the wise, when you're reading questions, and it's clearly going to be a question involving hypothesis testing. One of the assumptions is that you need to have a normal distribution to have a reliable result. And the thing to keep in mind is they may not tell you what the parent's parental, that's a good word, what the parent's distribution is. So if I said to you, typically this is one of the online questions, was so the distribution of wait times at Tim Hortons is normally distributed with a mean of this and a standard deviation of that. I just told you it's normally distributed. That means whatever test you want to perform is going to be valid, regardless of the sample size. However, if I forgot, let's say I didn't tell you, let's say I said the distribution of ages in an adult education classroom has a mean of, say, 35 and a spread of 7, blah, 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 what's the following values? I didn't say what the distribution was. I didn't tell you it was normal. I didn't tell you it had a skew. So if it's an unknown distribution, you have to look at the sample size. I'm coming up to the central limit theorem stuff here. I just want to warm you up on that. If I told you the sample size was 18, but I didn't say normal distribution for the population, you can't rely on the statistic that you calculate to be accurate or reliable, because we don't have evidence for a normal distribution, and these tests need that. The central limit theorem says had the sample been 30 count or more, it really doesn't matter what the parent distribution is. We're still going to have a normal distribution characteristic on the sample, and that's the thing to keep in mind. So let's go through and list the 4 bullet points for the sampling distribution properties for mean values, and I'm going to also do the 3 that are associated with proportions as well. Now, number 1, remember this is for mean values. Now I see they've added a little bit more explanatory information onto the formula sheet this semester. So property number 1 says the mean of y bar, in other words, the mean of your samples. I should explain this. We'll do this here in a minute. So the mean of y bar is equal to mu subscript y bar, and this is equal to just mu. And now I know you're saying, what the hell are you talking about? What does this mean? No pun intended, but this is what it means. We're going to take a side trip to explain the background on this. And I know my students are going, well, I know what you're going to say. You've already said it to me this week. That's fine. I'm thinking about people I haven't said it to. In the context of quality control, the naive and not effective way is to pull an item off a production line and measure it. It's either too big, too small, or it's just right. You know, Goldilocks and the 3 bears. Goldilocks? Goldilocks. Whatever. So the better way is to take a collection of items randomly selected off the production line at a time and measure them all. But that's not what you're going to write down. You're going to write down only the average of that collection. At the end of the day, you're going to have a collection of average values. That is the number that's being talked about here. So what this says is, and that's remarkably accurate too. We don't prove things like that in this course, but if you were to do an honors degree or pursue statistics in the graduate program, you would certainly understand this. So we're saying that the average value, the mean of y bar, is the average of all those sample means, whose alternative notation is mu with subscript y bar, is equal to mu. But remember, mu represents the population mean. So in the simplest form is, if you know what the sample mean is, you know what the population mean is. They are the same. Of course, you're going to say, well, wait a minute, it never shows up that way. That's right, because I haven't got to number 2 yet, which is the standard deviation. Because anytime you have a collection of values, there's going to be a spread. But theoretically, it can be shown that they're the same. All right, moving on to number 2 for this rascal is the standard deviation of our collection of y bars. In other words, the spread of the sample means in the theory that we're talking about. Oh, who we got going on here? We got yeah, we have random strings generated. Hello, random strings generated. Okay, so the standard deviation of y bar. This is calculated by the population standard deviation given by little sigma divided by the square root of n. And this is where that came from when I wrote the Z formulas down earlier. This is where the standard error came from. And the shorthand notation for this also on the formula sheet is little sigma subscript y bar. So this gives us the spread of our sample means that I was talking about when we collected items off the production line for doing quality control work. And what do we got going on there? Oh, I see Lorenzo's on top of that. Hello, everyone. Now, number 3 is simply a statement of the obvious. So it's we'll have to bring in Willa today for a cat. The peanut gallery over here is talking about liking kitties. We have lots of cats around here. It's the basic, the channel mascots are cats. So for instance, here we have a genuine stuffed Pusheen. Yeah, see that? Here, I'm gonna just check that out there. Can you see Pusheen? Ah, there we go. Pusheen. I'm on my way to something, 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 dark side. Okay, you know the meme I'm talking about. If you don't, look it up. All right, so the two most opaque statements on the formula sheet are for items number 3 and 4. So I could try to write down the mess, the terse mathematical notation, but I'm not going to, because why would I torture you? That's like me reaching out and going, I'm going to poke you in the eye. Poke, poke. You won't enjoy it, neither will I. So I'm doing this in the order it's on the formula sheet. So the third bullet point for mean value sampling property distribution, sampling distribution properties, translates to the following statement. If the population you're drawing your sample from is known to be normally distributed, then a sample of any size drawn from that population will also have the characteristics of a normal distribution. The implication of that is now you can go ahead and use the Z formula, you can go ahead and use the T formula, you can go ahead and do an analysis of variance computation. All these things rely on that normal distribution. So samples, I'm just going to write a quick note. So samples from a normal distribution, I'm going to use the shorthand I showed you earlier, this just means normal distribution, are also normally distributed. Bazinga, there we go. It's number 4 that we generally refer to as the central limit theorem. And if you go looking online, there's plenty of central limit theorems, so you got to be careful which one you read about. And again, I'm doing this in the order in which it appears on your formula sheet. This one, I'm going to translate again into a simple statement, says, if you have an unknown distribution of the population, or maybe you're told that it has a skew. Anyway, the point is it's not normally distributed. But your sample is 30 count or larger, then the sample will have the characteristics, and those characteristics improve as the sample size gets bigger, the characteristics of a normal distribution. So let's write that down in short form. For n greater than or equal to 30, non-normal distributions, non-normally distributed populations will have a normally distributed sample. That's not the best grammar in the world, but it gets the point across. In other words, if your sample is 30 or larger, you're good to go. If it's less than 30, the result is somewhat sketchy. Okay, I'm going to make a picture to describe this. How am I doing here on the clock? We're doing all right. We're coming up to 2 o'clock. I got time to do what I wanted to do. Let's get this done here. Okay, so we have colored chalk today. So this will allow me to make a nice picture. And I will describe it. So if you want to make notes and things without having to look at the screen, I'm going to narrate what I do. So we're going to have 2 pictures. Let's make the first one. The white chalk is representing the population distribution, and I drew a normal distribution. Okay, so that means there's a center, and the center is labeled mu. I put an equal sign on that. Now, coming from the center, I have arrows going to the left and to the right. This is the spread, which is little sigma. Now we're going to shift to another color. I have color choice here. Look at that. Let's go with this. Let's go with this blue one. I think that'll be a good one. Now, if I let blue represent the sample, then my center mu is equal to y bar in blue, but that, now remember, for those of you who have done calculus, the area under these curves is exactly 1. So if I'm squeezing the tails down, then the center has to go up because the area has to always be 1. So in the with the blue chalk, I drew a blue line right beside the white line for center, but I extended it above the curve a little bit. And now I'm going to do a bell curve coming off the high point. So what I'm saying is, because the sample size is anything other than 1, I'm going to be dividing a larger number. I'm going to be dividing by a number that gets larger. So this means the spread of the sample has to shrink. And if you've done calculus, that's simply as the denominator goes to infinity and the numerator is constant, the limit point is, or the limit becomes 0, or it becomes effectively 0. It won't be exactly 0. So in blue chalk, then I'm going to write that the spread of the sample is sigma over square root n. And this is properties number 1, number 2, and number 3. Are you chomping at the bit? He's chomping at the bit over there. Okay, now let's look at how this works otherwise. Now I'm going to make a right tail distribution. So clearly this is non-normal. The center is going to be to the right of the hump. We'll call that mu again, so mu. The spread, of course, is an arrow moving out from left to right to describe the width. I'll use little sigma for that. Now, how does this work when n is sufficiently large? Well, the center is still the same, so mu is equal to y bar. But now I'm going to have a reasonable bell curve around that center point with a spread given just as I did before with property number 2. I'm going to slide that in here. So sigma over square root n. But this is for n greater than or equal to 30. Whereas up here, the first picture was n greater than or equal to 2. Because you can't have the average of a single thing, right? Okay, so for my second picture here, this is properties number 1, number 2, and number 4. And if that's all you need to understand sampling properties, sampling distribution properties for mean values. The properties for proportions I'm going to throw up here in just a moment, and then we'll carry on here. What's this say here? Does z-score map a normal Gaussian distribution of mean mu and standard deviation to a standard normal? Yes, it does, because all you're doing, so if you're going to couch it in mathematical terms like that, whenever we're essentially normalizing the differences. The thing to remember is in the final analysis, Z represents, well, any test statistic represents the number of standard deviations you are above or below the mean. So the reason we call it the standard normal distribution is because by dividing out the standard error, we've standardized the thing. So now we've taken a problem that has numbers that are specific to the context of the problem. But if you wanted to try to analyze that, and you didn't want to do the calculus to compute the p-value, you would have to have a book of Z tables for every possible configuration of numbers, which is clearly impossible. So, and this applies to the other test statistics as well. But by always dividing out the spread, so you've got the difference between what you measured and what you expected to see, and you divide out the spread, now you convert to a common yardstick. And now you can have one table to look up p-values. Or you can just take the raw numbers, plug it into the integral, and figure it out yourself. But I don't recommend that. Unless you're a nerd, then go ahead. And there's nothing wrong with that, by the way, no judgments. Okay, let's move on to proportions. So yes, if you want to say map to, I guess that's true, you do map it, because one thing leads to another. But as with a lot of things, you know, using the phrase mapping comes from, you know, if we're talking about things in algebra, so you're taking mapping from R2 to R3. Well, yeah, you're converting, right? So that's essentially, we're making a conversion. Okay, so proportions is all about percentages. It's just typically how we handle count data. So if I have 100 people and 37 said that they didn't agree with what I was talking about, then I would say that The percentage or proportion of disagreement is 0.37. So that's the kind of data type we're working with here for this particular set of rules. So for proportions, let's see what we have. Proportions. Why is this a hard word to spell? I think there's a brain cell missing in action here. So property number 1 is identical to what we saw for mean values. Actually, properties 1 and 2 are identical. They mean the same thing, just the notation's a bit different. So the average value of our p hats, I'm going to explain this in a minute, is equal to mu of p hat, which can also be just written as lowercase p. So the rationalization here is exactly the same as what I mentioned earlier. Let's say you want to conduct a survey and see what people think about something, and doing the broad theoretical sense. Is this going on YouTube or Twitch after the stream? I think it's going to go on to YouTube for sure, and I think it's going to end up also archived on the Twitch channel for now, and probably will end up on Patreon as well as an archive site. We're having a couple of technical problems with what we want to do, so that's why a small change in plans. And that's, yeah, okay, good. Okay, so what I'm getting at is, let's say you want to survey people on campus. Well, the University of Alberta is a very large campus, so you get 10 people and you say, okay, once you guys spread out, go to random locations, don't come back until you've interviewed 20 people, or 30 or 10, I don't care, just go interview people. Well, every person that comes back is going to have their own unique measure of agreement to a question and measure of disagreement. So p hat typically measures success, and 1 minus p hat measures failure. And those two things have to add up to 100%. So you're going to come back and you've got a collection of 10 results, 10 average values. Because if, say, person 2 went out and came back with 29 responses, well, you can take the average. Well, no, you wouldn't take the average. You'd have a p hat there, and person number 3 would have a p hat, and person number 1 would have a p hat, and you're going to take the average of the p hats, and that's going to be notated by mu with the subscript p hat. And just like when we were talking about mean values, when we do it this way, theoretically, the sample p hats, the sample proportions, will be centered exactly at the population proportion. This is how public opinion surveys, when done properly, provide very good results when you want to estimate public opinion. There's always room for error. This is statistics, after all. Nothing's exact. So you always have to consider the margin of error. But we'll talk about that tomorrow when we do some more computation-based statistics. I'm thinking about confidence intervals on that one. Okay, so the point is, if I know that 37% of people in my sample say yes, they agree with a question, I'll be pretty sure that the population is 37% in agreement as well. Now, how about a standard error? We need that. Number 2, SD bracket of p hat is given by a square root function. So we have a rational expression under a square root. We have p hat times 1 minus p hat. So this is always the success percentage times the failure percentage. It always works that way. And then you divide out the sample size n, and you're done. That provides your spread, your measure of spread, your measure of variability in the topic. Now, there's only 3, not 4, properties here. So bullet point number 3, again, is written in fairly terse mathematical notation. So the simple translation is this. For you to have a normally distributed sample, in other words, a sample that you can reliably compute p-values with and expect a good result, you need a minimum of 10 success conditions and 10 failure conditions, which of course is a sample size of 20. But this is only going to be valid when p is 0.5. The further p and 1 minus p get away from 0.5, the bigger your sample is going to have to get. And I will demonstrate that in a moment. We call this the 10-10 rule. So let me write that down. For a normal distribution, or for a normally distributed, that's going to be p hat comma, square root P1 minus P over N. So for a normally distributed sample, we need 10 success and 10 failures. So in notation, and the notation on your sheet is n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. This is what you got to do. And you may be asked to do an assessment. They'll give you some numbers, give context to a question, and say, okay, does this meet the criteria for a normal distribution? Can you trust your sample results? And you're probably going to have to do this computation. So let me demonstrate how this works. And then I'm going to wrap up here and turn this over to Adrian. It must be 2 o'clock by now, gentlemen.
Yep.
Okay, so let me do a quick demo on this little property, and then we'll, do you have a cat to bring in for the dog and pony show transition? Let n equal 20, and p is equal to 0.5. So if p is 0.5, then 1 minus p must also be 0.5. So I'm going to show you where this works. And then I'm going to show you how it breaks. So we need the 10-10 rule to be verified. So we have 20 times 0.50. Well, that's equal to 10, and that's fine. And then I have 20 times 1 minus 0.50. Well, that's just 0.50, and that's equal to 10. So this is where the 10-10 rule works. Now, as soon as we vary from that, let's call this 40, and this one 60. Nothing else changes. So 20 times 40, well, now that's only 8. 40% of 20 is 8, and that's too small. And over here, 20 times 0.60 is 12. That's still fine. But now you need a bigger sample because you need both conditions to be true. If they're not, you can't trust your result. So the idea is to verify if you're asked to. Typically on the exam, they want to see you do something more involved, but you can't make every exam question ridiculously hard because, well, that's kind of cruel. So sometimes you get these little easy questions like this where it's a simple computation. You don't even need a calculator, really. I mean, come on. What is 4 times 2? It's 8. Move the decimal. You don't need to make this hard, okay? And that pretty much wraps up the central limit theorem discussion, and that's what I wanted to talk about today. And, you know, along with the discussion we had with some of the definitions, there's a few more definitions I want to go over. But when we do this again tomorrow, same time, same channel, I'm going to do more computations, particularly the more complicated ones where we're comparing 2 samples. But we'll talk about a variety of things. With that in mind, I think we should probably turn this over to Adrian, because I'm pretty sure he's got a number of things to talk about. Shall we have a musical interlude over here? Or, no? Oh, you're not quite ready to go yet. If you're wondering what's going on, he's playing Mario at the moment. What's that, Lorenzo?
You want to plug Patreon?
Oh, yeah. Okay, so just as a heads up, I'm always forgetting to, we're trying to establish a Patreon clientele to keep the channel going. YouTube doesn't pay people anymore. If you look at all the big channels, ones you think will be rolling in YouTube bucks, they're not. They all have Patreon, they all have PayPal, they all have other sources of support. We don't have anywhere near those huge numbers. I think we got like 2,500 viewers or something, regulars on the YouTube channel. So we're trying to move things over to Patreon. We're also on Twitch, obviously, but if you would support us on Patreon, that would be a great thing. We're not asking a lot. There's a statistics book I wrote on our Patreon account. It's 220 practice questions with complete solutions. I just don't get, well, the answer is 6. No, I'll tell you how to get the answer 6. You can find it on there.
3 factorial.
3 factorial is building 6. I was giving Adrian a hard time because at McEwen, being the creative bunch that they are, they simply give their buildings names like Building 1, and Building 2, and Building 6. So the other day I said, well, you're in Building 3 factorial. And of course went whoosh
I
over
thought
his
you were
head.
just excited to say building 3, and I was like, no,
No.
there is no building 3. Technically, it's the street that they're on. But the building 5 is on 105, building 6 is on 106.
It still sounds very anally retentive.
10, 9, 8, 7, 6, 6, 6.
I like my factorial idea better.
I do.
Building 5 factorial, what's that?
You know how many ways there are to sing the alphabet
He's
song?
ignoring me.
26 factorial is a big number.
It is a very large number.
Who in the fucking Ethan's on here?
I'm going to flip you over here.
Oh,
Okay.
you're going to flip me off? I thought you said.
No. I don't touch that stuff. Did I show you Pusheen? Pusheen.
What is Ethan saying? This is going in my personal encyclopedia?
I hope so.
Oh, because I was trying to write unmolested in our group chat, and it wouldn't autocorrect it because it's censored.
So, what else do we have around here for entertainment value? Because he's busy doing stuff that no
What are you
one wants to
talking
know.
about?
Well, I'm just looking at this.
I'm going to put my coffee here again and see if I can spill it.
What do we have here? We have
Whack
avocado
avocado.
smash. It's not like Mr. Potato Head, I hope. And it's not an eggplant.
It's a game. It's a game.
Okay, no one's laughing at that.
Nobody's laughing at you.
Nobody laughs at my jokes.
Now go away, or I will taunt you a second time.
We already have one.
I told them we already got one. Where did I put that? I don't know where I put it now.
Where you laughing?
I was showing the things that all the students gave me as
yes.
gifts.
Oh, where's the other one? I will find it.
That's there it is. I see it.
I'll get it.
And the socks. Can I get my fancy socks up there? Einstein socks. What did you get from your?
I'm not ready to do another 2 hours.
That one's a cat. Yeah, I wasn't ready to do 2 hours anyways. We'll see how far we get. Only Alessandra paid, so we're not doing 2 hours anymore.
Oh, yes, we are. I promise the world.
She's on. Okay, good.
Yeah, right on.
Okay, we're gonna start. Let's start. Put
Okay.
that back. Put that back. Kitties. There's a whole row of cats. I'm gonna put this knot here. Let's put this over here. Oh. Rock, paper, scissors, lizard, Spock. That's the complete graph. Okay, what are we doing? You're like, I don't know. Now I gotta read off. Let me get.
It's in the email, right?
I know I'm going to Gmail right now. Yeah. What's this? Somebody's following us. Okay, good. Math sample. What's Alessandra want first? What do you want first? Let's do yours first. Is she gonna say something? Yeah. Alessandra RR212. I see what you did. I won't say your last name, but because of FOIP. I can FOIP whatever I want on Twitch. I also was going to do... Ooh, maybe we should do that. I don't know. I didn't prepare at all. That's what I'm saying. We want to do Tim's eigenvalues and eigenvectors. Let's look at the first one, and then I'll do the other one. Well, I can spit off that one that Lorenzo and I just finished. But he was saying do the complex eigenvalue ones first, right? Tim?
I just thought I was having a chit chat with the producer. What's
That's
that?
all right. He wanted you to do complex eigenvalues from
Yes,
this,
that's
right?
right. What was the,
-2, -5. I'm copying it down right now. 10, 8. I am pretty sure I'm allergic to chalk. I'm going to sneeze immediately.
Oh, well, no.
That's all right. I
Sneezing
like
in
that
yourself.
noise. So we're going to do from our class. You don't have to worry about complex eigenvalues because I'm not mean like the University of Alberta. But it'll be the same technique. So what we're going to do first of all is find the eigenvalues from this. They're going to be complex this time. You don't have to do that, but the process is exactly the same. So you can follow the idea and the process of what's happening. You just have to guarantee yours will be real eigenvalues because I was nice. So it doesn't change, but it's going to look different, but it doesn't change it. The determinant of negative, or so let's do this. This will be lambda plus 2, 5, -10, lambda minus 8. And we want the determinant of this. So this is going to be what? Lambda plus 2, lambda minus 8, plus 50. So that's going to give me a headache. Lambda squared minus 6. Oh, no, they're going to make me do arithmetic. Minus 6 lambda.
Plus 34.
Plus 34. Not 43, 34. And so then is that not going to factor nicely? Because you had minus 16 plus 50, right? Yeah, okay, that I agree with that now. I still had to calculate it. And then now I'm pretty sure they're complex eigenvalues. So now what I'm going to do is complete the square. So I need b. If I don't know how to factor this, you can always use the quadratic formula. I'm going to use b is equal to negative 6 over 2 is going to be negative 3. Squared is 9. Because I have that, I can either add the 9 or what we can do is this. We're going to do lambda squared minus 6 lambda plus 9 minus 9. Okay, smarty pants. 34 and minus 9. Tim's not listening anymore.
Oh, I am. What's up?
34 minus 9.
34.
20 into 4.
25.
What?
25.
25. Yeah, you're right. I also got 25.
Good man.
I'm using him as backup because I'm notoriously bad at computing numbers. I'm not looking for this on the exam. I'm looking for method. So what that gives me is, but do you see it's a plus? So it's lambda minus 3 squared plus 25. And now we're looking for 0. So it did give us a perfect square, but on that multiple choice, it says which eigenvector are we going to get associated to this? What they're saying is now we get, if I'm looking for this to be 0, this is going to give me, we complete the square, but now I have lambda minus 3 squared is equal to negative 25. So when I square this, this will be lambda minus 3 equals plus or minus 5i, which is the square root of negative 1. And the square root of 25 is 5. So then that means lambda is equal to 3 plus or minus 5i. And so now it gave me an eigenvector, but how do we find the eigenvectors associated to these complex eigenvalues now? This one says, let's do one of them, and then we can get, this is 3 plus 5i. Oh, fuck. I just erased it. Frick. Damn it. Why did I write? On your exam, don't erase that piece. Now I have to find it again. Where is this? How come I can't find it again?
The answer is 3 minus 5. So the vector is negative 1, comma 1 minus 5.
I know, but I don't. Well, that's given us 2 choices. Just wait. I'm not looking at, there's no such thing as multiple choice on an exam. Why would I look for 3 false answers? I'm just going to do it the way that I want. It's this guy. And so what do you do with this? You have to do lambda plus 2, 5, negative 10. I'm going to show you how to do it in case you need to do it on the exam. This is a good strategy, so I'm glad that you said that. And what he's doing is he's reverse engineering based on the fact that you've got all the answers in front of you. Do that, but I disagree with this wholeheartedly. So, just a second, did I do that right? Is that correct now? Now that you have this, regardless, I'm going to get what he said, but I'm going to ignore a strategy on an exam that has multiple choice. I think that this is horrible that they put multiple choice on a math exam or an ENIG exams, really, because that just means they're being lazy and they don't want to mark 300 people at a time, which they're force feeding you. So instead of that, ignore all the answers. There has to be one correct answer. I'm not going to look at them, and I was purposely not going to look at them. I'm going to show you, regardless of whether it's complex or not, how to row reduce this. So what I have to do is put that in there. I'm looking for, and from one complex guy and the conjugate, because they have to come in conjugate pairs if they're roots of this polynomial. So they came in conjugate pairs. The other one was 3 minus 5i. But one complex solution will give you 2 linearly independent real solutions if you're trying to diagonalize this, if you get complex eigenvalues. But for now, let's see. We have to put this back into here is what I wanted. So I'm going to get 5 plus 5i, 5. And then I have negative 10. And then I have, what do I get? Now I'm adding in my head. Negative 5 plus 5i equals 0, 0. We're looking for the null space of lambda I minus a. And so now how do you do this? Is there suggestions? Or they're not watching anymore because I started doing the complex eigenvalues. So what I would do is, because I have a negative 10 here, is I would interchange these two rows unless you want to know how to do complex inverses. So I'm going to write that as negative 10, negative 5 plus 5i equals 0, 0. Oh, scratchy, scratchy. And then I'm going to write, this is what I was saying also, you have to be able to kill one of these rows, which you can. You can kill one of these rows. So the row has to go to 0. And then if I want a leading 1, or if you want to see how I did that actually, let's multiply it out, 5i, and then, where is this, 5. So I can get rid of this by multiplying by negative 10, which is going to give me what? 1/2 minus 1/2 I. And then I want to multiply this row by 5 plus 5i negative to get rid of it. What's going to happen to that? We're going to get 1/2 minus 1/2 I equals 0, 0. And then I'm going to get 0. And then what happens to this hot mess? You get 0. It has to be 0. It has to be linearly independent. For that to be an eigenvalue, the determinant has to be 0, and especially when it's complex variables, I always tell the student, fake it till you make it. You have to be able to kill the row. If you do that and FOIL that all out, it will exactly equal 5, or negative 5, and then you'll get this to go away. If you want to see what we're doing is we're multiplying 1/2 times I times negative 5 minus 5i, and you have to FOIL all that out. What's that going to give you? A headache probably. But then that gives me negative 5 over 2. And then what did we get? Minus 5 over 2i plus 5 over 2i, which cancels. And then I get negative 1/2 positive 1/2 5i squared. But then that's what? Negative 5 over 2 minus 5 over 2, which is negative 5. Whoa. Ha 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 ha! I moved the coffee this time. I moved it. I spilled something else, but it wasn't the coffee. Give me that. I spilled all my stickmen, all the things for playing games, all these sticks and all the puzzle games, because I like puzzles and games. Not this time. Say, don't worry, it wasn't as bad. It wasn't as bad. But I saved my coffee. My butt hit it again. That went right up rectum hell. Damn near killed him. Seriously, the corner of the table just went up my ass. Fuck. But I do like eigenvalues. That's what you get. So negative 5. Do you see all that algebra that gave me? So what did we get? This, when I multiply this by this, you get negative 5 plus 5 gives me a 0 right here. So then you add 5 plus the negative 5 from that computation, which gave me a 0. Okay, good. Ow, my bum. Smarty pants. I did all the algebra. So that, but do you see now that was the moral? Fake it till you make it. You have to have a row of zeros. What does this say now? This says that this will be the free variable t, and then what do I have? A headache that says 1 times x1 plus 1/2 minus I over 2 times x2 equals 0. So then that's going to give me, that says 1 is equal to negative 1/2 plus I over 2 times t. And so the eigenvector associated to this is going to be what? Oh, I see what they did. They did the dirty trick also. So that's going to give me, I like secrets. This gives me 1/2 negative 1/2 plus I over 2 times 1 times t. And then what do I have to do? If I pick t equals, is that one of the solutions? Or is it the other one, those dirty sons, those dirty dirties? I did all that.
The other one, I think.
Yeah. So now what the heck?
1 minus I? Yeah, 1 minus I.
Yeah. So that concludes, if I made t equals 2, that would say that what would I get? I would get negative 1 plus I, but then I have a 2 here, which gives me, I'll just show you, that gives me negative 1, 2 plus 1, 0, I, and there's the 2 linearly independent vectors and the real solutions associated to the 1 complex eigenvalue. I refuse to do what they did, and this is why multiple choice on an exam is mean. What that means is now you can conclude that, because technically if you're on the exam, I would just switch to that now. But because I picked this one arbitrarily and I didn't get the eigenvector that they were looking for, it has to be the other one. So it has to be associated to 3 minus I now. I want to keep going and do that again, though, because I like complex numbers. The real numbers are complex. Oh, I did it again, son of a bitch. What is it? Am I looking at the... No, it's lambda plus 2, 5, negative 10, lambda minus 8. So now if I put the next one in there, you can see what are we going to get? We're going to get 5 minus 5i, 5, negative 10. Uh-oh, I should probably do this slower. And then what do I get? Negative 5 minus 5i equals 0, 0. Which again, if you want to find the, do you want to do it differently now? How do I find the inverse of this, Lorenzo? Didn't you take complex variables?
This one, you divide by the conjugate, no?
Right.
Or multiply by the conjugate.
Multiply by the conjugate over the conjugate. So what's that going to be? 5 plus 5i over 5 plus 5i. So first of all, what I'm saying is, what's the inverse? What's 1 over 5 minus 5i? I want to multiply by 5 plus 5i over 5 plus 5i. What does that do? This will give me the modulus, which will be 5 plus 5i over, what do I get? 25 plus 25, which is, what in the frick are they doing to me here? 5 plus 5i over 50. That's not so bad. That's what? 1 over 10 plus 1. Did I do that right? 5 over 50 is what? No. Yeah, okay, yeah. 1 over 10 plus 1 over 10i. Are you sick of looking at that yet? Do you see why I interchanged the rows and did that? So then that's that guy. But what do I want to do? That's the inverse of that guy. And then, so what do I have to do that? If I want to make that a 1, so I just found that guy. That's the inverse of this guy. And so if I want to multiply by that to get a 1, that's going to be now a 1 in that spot. And then it should be 5 times 1 over 10 plus 1 over 10i equals 0, 0 times negative 10, negative 5 minus 5i. And then now that should be good. And then what does that give me? A headache. That gives me 1 plus, or not plus, 1/2 plus 1/2 I 0, 0 equals 0, 0. When I kill that row, I'm speeding it up now. And then what did it give me? This is the free variable. So then it should give me x2 is t, x1 is negative 1/2 minus 1/2 I times t. So then that means x1, x2 as a vector should be equal to negative 1/2 minus 1/2 I times 1. Did I do something wrong? Why are you whispering? Just say it out loud so I can hear you.
We're talking about the book that we're writing.
Okay, you're writing about the book. Did I do that wrong? No, that should be. Oh, I see what they did. That's dirty. Times t. And then so now they're finding the inverse of that guy. Oh, I see what they did. Yeah, that's mean. Those guys are mean. They're multiplying by the inverse to get this here, which when I multiply that is going to give me -1 and then 1 minus I. So yes, it's definitely this one. It's this one is the long story short. I picked a t value which would be the inverse of this. T to be 1/2 times 1/2 I inverse, and then it will switch the places of those, which will give me, and then they're multiplying by -1 also. That was pretty mean. But it's 3 plus 5I. All right, complex eigenvalues.
Alessandra's asking a question. I'm assuming you're done with that one now?
Yeah.
Yeah, so Alessandra's...
I'm gonna. I can't see now. Let's do the other one. I have no idea what that means. You have to. What does number 1 from midterm 2? I don't remember what that means.
You need to find the length of u plus 2v, the vector's norm of u.
Okay, she's writing it out. Yeah. I can go over this because you paid, but it's not on the exam. I made you do area on the exam. So we want the length of u plus 2v, where it gave me, what's the angle between them? 60 degrees. Ugh, this chalk. Stop. I gotta do like the poopy hand and the clean hand for handshaking. Equals 1. The norm of u is 2. And v is a unit vector. So first of all, what do we know about squared? That's dot product with yourself. So this is u plus 2v dot product with u plus 2v. Now using the rules, you can FOIL this, which is going to be u dot u plus 4 u dot v, because I can turn them around, plus 4 v dot v. Norm of u is equal to norm of u squared plus 2 u dot v is the norm of u times the norm of v times cosine of 60 degrees plus 4 times the norm of v squared, which is equal to, now I can put the numbers in. This is 4 squared plus 4 times 2 times 1 times cos of 60 degrees is what? 1/2, that's correct. Plus 4 times 1 squared, which is equal to 4 times, cancel 4 squared is what? No, I already did that twice. That should be 2 squared. 4 plus 4 plus 4. 34, 20, 12, 16, 12. But then what is it, should it be?
What is it shouldn't be?
What is it shouldn't be? It shouldn't be 12 because it's what? Squared. There you go. Was why would I do that though? I'll do that, but why would I do it?
So you could say that the decimal version is
1.73. 1.73 is the square root of 3, and then I could multiply it by that, and then now we're doing freaking things I don't like to do, which is going to give me 6, 14, 3.46.
Where did I hear that before?
What did you just say?
3.46. Where did I hear that before?
You've done this before. You didn't do that in your head faster than me, did you?
I'm just saying.
Tim's good at math too. They can't hear you. They think I'm talking to myself now. I'm going to sneeze. While
he's sneezing, I'm going to mute his mic and we'll chat. Now they can hear us.
Okay, what else does she want? I can neither confirm nor deny. Weren't you at the review yesterday? If I didn't talk about it in the review, it's not on the exam. I showed you all the categories. Well, length in some way, shape, or form is on the exam, but what's the... Ugh, this chalk. I don't know if I could do 2 hours of this crap. I'm gonna... Fuck sakes. I'm going to sneeze my face off today. I don't know why it got worse all of a sudden. Is it the new chalk? Whoa.
Well, maybe.
I don't know. It just is bothering me today. Whatever. I'll tough it through. Next. Well, you find another one. What are we going to do? It says B is a matrix which has eigenvalue 1 associated to U and eigenvalue -1 associated to V. And then it says explain my... Carefully, not willy-nilly. I'm not going to do it carefully. I'm going to try and jam this table out my butt again, which is uncareful. Oh, there. That's why I moved the table. I bent the table with my butt. So, so let's do this in general. If Bx equals lambda x so if lambda is an eigenvalue of B, why is lambda squared an eigenvalue of B squared? I'll just do B squared. What's B squared? X. That's just B times Bx. But what's Bx? Lambda x. So that equals B times lambda x. And then I can associate that, bring the junk to the front, which is lambda times Bx again. But what's that? That's this again. So that's going to be lambda times lambda x, which is lambda squared x. So what that says is B squared x is equal to lambda squared x. So x is an eigenvalue of B squared associated to lambda squared. So if we know this is true now, what that says is B squared times U is equal to 1 squared times U, and B squared times V is equal to -1 squared times V. And then I wanted to show that U plus B was an eigenvalue. So what do I want to do? It's associated to 1 also. So then B squared times U plus V, which is 1 times V, which is also V. This guy and this guy, which is also equal to U. Then this will be B squared times U plus B squared times V, which is equal to, because of this, U plus V, which is equal to 1 times U plus V. Therefore, U plus V is an eigenvalue associated to this. And then it says be careful, and somewhere in your argument tell me why U plus V can't equal 0, because eigenvectors associated to distinct eigenvalues are linearly independent. And if this was 0, that would mean that U equals -V, which says that they're linearly dependent. So U plus V is an eigenvalue of B squared. That's off of the U of A's final exam, not this one. Holy crap, I'm going to frickin' sneeze again. Sneeze break.
He's muted. He can sneeze as he pleases. There's a rhyme there. Sneeze as you please.
Okay.
I think we can switch back to the
I don't know if
Or from Thomas the Tank
depends.
Engine.
I found a kitty. I don't know if you can see the kitty.
It's there. Yeah.
All right, now what's next? Whew.
You want to go through intersecting planes intersecting and the line of intersection? I'm just throwing one out there just because we have time.
Okay. What did you say?
I said the line of intersection of two planes. Did I say that correctly?
Yeah. Okay.
You want to do the one from the assignment?
I was gonna make it up, but
Sure. Yeah, go for it. Yeah.
you've got plane 1 and you got plane 2. linearly independent. What's the definition of linear independence? If alpha 1 u plus alpha 2 v equals 0, this has to imply that alpha 1 equals alpha 2 is the unique trivial solution. But if I look at that, if u plus v is equal to 0, I already know a priori that u and v are linearly independent because they're from distinct eigenvalues. But if this was true, that would imply that u is equal to negative v, so they would be dependent. So then that means that they can't be, this means that u plus v can't be 0. Otherwise they would be dependent, but I know that they're linearly independent. All right. Does that make sense? Again, I don't really care if they're listening at this stage, but McEwen tries to pretend that they're just as good as the U of A, but the U of A's exam looks way worse than any of the ones that the McEwen gives them for the most part. It looks like they're just trying to torture people. Again, I think part of this is the way that they phrase this and word all of this kind of stuff is so that you can't just use AI to try and practice this, but then it's like, well, now you've lost everybody from this I'm going to sneeze again. I've lost everybody from this assignment, or what was I saying? I don't know. All I can think of is this chalk is trying to make me sneeze every time I use it. Just keep using it. They're trying to make the wording of the exam questions convoluted so that AI can't do it immediately for you, but they make it so convoluted that the student is lost too, and the instructors. And then they're changing in that one, the multiple choice that I did, this is me. So let's go through the multiple choice before I do the plain one. I'll do this. But what they're doing was they gave you multiple choice. Okay? Which I disagree with wholeheartedly, because the joke is, why would I come up with 3 wrong answers to a problem? I like to find the correct solution to a problem, which is stupid, finding 3 of the wrong answers. But then what they did was, when I get an eigenvector, it'll be, say, x1 times x2 times t. And then I did this in the review in my class too, because at one point, say you'd have like a negative 3 over 2 is the one that we had, and then a 1. But what that means is this line is invariant under this linear transformation, this line L. And then what's a basis for this line? Any vector in the direction of that line is a basis. And then I can uniquely describe any other vector in that direction from this guy because it's a basis in one dimension. So what they're doing is, if you don't want fractions, I say, you can take t equals 2. And then I could get the vector negative 3, 2. And then so now I can say that this is an eigenvector associated to that eigenvector. So what they're saying is, if ax equals, I can't remember what it was now, but let's pretend it was a 4. I'm pretty sure it was a 4, right? Because it was geometric multiplicity 4. And the one that we were doing yesterday in class. It doesn't really matter. But say I'm saying that ax is equal to 4 times, and the x is this vector. So negative 3 over 2, 1 is equal to negative 3 over 2, 1. That says that this eigenvector is associated to this eigenvalue. But I can also do this. I can say that this one is also, because it's in the span of that guy. You can pick anyone to be in that invariant subspace. You can pick anybody to be a basis for it. So negative 3, 2 will also do that. Any vector in that direction, it's saying, when I hit it with A, it'll get stretched by 4. So you can use the one with fractions, but this is really confusing the first time you've done this. And they do it right at the end of the class, and then they do complex variables. And then so the dirty that they did on that practice exam to you, which I really disagree with, was what they did was you get, say, negative 1/2 minus 1/2 I times 1, but then it's times t. And what they did was they gave you one that had the coordinates where the complex number wasn't here, and they switched it to here. But what did they do? They picked a t value to fudge that, to get rid of it, and then that one's there, and then you're confused as all heck, and then it's hard to see which one was in there. And then that's just trying to be mean and confuse people. That has nothing to do with learning. That's a stupid education game. So this is why you want to come and start paying on Patreon. I'm going to show you how to survive the weird, stupid tricks that they're trying to do and the dirties that they're trying to do to you online. You're like, tone it back.
No, I was going to say, I've got here's a math question. Wait a minute, I got to talk to the microphone over here.
Oh yeah.
So I got a math question from.
He's like, you don't have to be a dick about it. I'm gonna sneeze. Okay.
So this is a math question from second semester calculus question for the Faculty of Business.
Okay.
Lagrange multipliers. You want to have a go at that?
Right up the go. I don't know how to do Lagrange multipliers
Oh, okay.
again.
We can leave it if you don't want to.
So you want to optimize?
Yep. Subject to a constraint,
Yeah.
and then explain why the system doesn't work, why the method doesn't work.
And then I gotta do what?
Need a book?
Yeah.
Hang on.
The
I'll get
hell
it.
are you
I got
doing?
it, I got it.
What are you doing to me? One at a time. One at a time. So, as he's getting me the book, let's do this one too, because this one will be for Alessandra, because this could very well be on the exam. So then we have two planes intersecting P1. What is this?
That's the Lagrange multiplier one.
Explain why it fails.
Yoo-hoo! Here we go.
Explain why it fails. What I don't know what you mean by explain why it fails.
Apparently, it doesn't find a.
Because it's a saddle point, or what are you
Probably.
saying?
It's probably a saddle point.
Okay, just a second. One problem at a time.
All right, we'll just leave that for now.
Whoa. Is that somebody asking or what?
That's on a practice exam that's current. But do this first. Do this first.
I thought of all people, why are you trying to throw me under the bus? Just a second. Yeah. Okay, now see, this is also what my brain does. Now we got to do this one first. You just load me with a question that I don't know how to do, and now my brain goes, now I have to solve it. Because, yeah, I have to cook up the stupid frickin' lambda 1 and lambda 2. So where's my f? Oh, f is linear. Oh, no, f of xy. Oh, yeah, okay, it's bilinear. So it's 3x plus 5y. And then what's my constraint? My constraint is this stupid guy, which is x to the 1/2 plus y to the 1/2 equals 4, which is 16 to the 1/2. Talking is better. The whispering just screws with my head. What do you want? So the constraint is, what we're doing is the gradient of f should equal lambda times the gradient of g, where g is the function, right? And then g should equal the constant. So what is the, oh, so then that should be, no wait, what? But they didn't, oh, is this g? This is g of xy, right? Equals, I shouldn't do that smart ass to myself. So, what are you asking me? Step one, if you don't know how to do it and you don't remember, look at the book. So first of all, what's the gradient? The gradient of f should be fairly easy. I'll do it the way that they like to do this in calculus, but this will be the partial of f with respect to x, and then the partial of f with respect to y will be the coordinates of this, because this is vector calculus. So the gradient of f, which should be a vector, is going to have, oh, and then we have the gradient of g. Is that why they're saying this? And then, okay. And then this is the 4. So just wait, let's calculate this piece of this first, and then we'll do the constraint. So then the gradient of this should be fairly easy. This should be 3, 5. Oh, is that what they're saying? And that's why it should fail? Okay, so now I have the gradient of f now is, just wait, it was 3, 5. Now I'm going to need more room. And then what's the gradient of g? The gradient of g is going to be the partial with respect to f, so that's going to be 1 over 2x to the 1/2, 1 over 2y to the 1/2. Is that right? Yeah. The partial of g with respect to x, the partial of g with respect to y, and then we want to set those equal to each other. The gradient of this should be, there's the lambda, right? And then we have to find the lambdas on the boundaries and all of this. The lambda of g. Why do I have to do this on Saturday? Because I've been fired from McEwen because I'm too top G. This is going to be 3, 5 is going to have to equal, really? That's what they did? That has to equal lambda over 2 root x, lambda over 2 root y. So then we have to say that is that y? This is well, because just wait. Let me finish rephrasing it. So now I've calculated the constraint. So the first constraint is, because this is the two-dimensional Lagrange multiplier. So we needed 3, 5, which is the gradient of f, to equal lambda times the gradient of g, which is lambda over 2 times 1 over root x. But it's giving us a 0 value, which will have a discontinuity, I think is what they're saying, right? Times 2 over root y. I thought you were going to make me have to, because as soon as I see this, it's like, now you're going to make me have to solve for all those boundary conditions. But no, that's not going to be as bad. They're not being as mean to me. You may still have to do Lagrange multipliers on the exam, I guess. So then there's the constraint. And then the other one we need is the constraint that it's on that weird root x guy times root y guy equals 4. So then this is root x plus root y equals 4. That's the Lagrange multiplier. Because we want to know when the gradient, the rate of change of the gradient is equal of f is the lambda times the gradient, a multiple, so they're in the same direction, right? The gradient of f is a vector. And if we're saying lambda is the gradient of g, that means that they're parallel and they're collinear because they're multiples of each other. So we're going to be in the same direction, but now with the constraint, this guy. But then it's saying find a constraint. Extremum. Wait, what? Oh, so they are making you do it. So first of all, well, shit. Does that work? Now I don't know what you're talking. A, find a constraint extremum. And then the other one, they're saying it doesn't exist as 16. B's easier because if I do this at 0, I have division by 0, which is bad. But now you're saying A, now you actually want me to do friggin' work. Now I gotta say, well, if these two vectors are equal to each other, that says 3 equals lambda over 2, 1 over root x. And 5 is equal to lambda over 2, 1 over root y. That, you want me to solve that? I don't want to do that. Okay, let's try it. What does that say? Is that what I'm doing? Because, yeah, then I'd have to go through all the cases. Extreme values of f from... Yeah, those are non-trivial equations. So, okay, definitely can't have x equals 0, but let's solve this so I can bring the root x up. And then that says lambda over 6. Am I right? And let's bring the root y up. And then that says, am I doing that? Lambda over 10.
If you add the two equations and then set it equal to 4, will that let you solve for lambda?
Ah ha ha. I was going to be like, now we have to be clever, but yeah, now Lorenzo's being clever. That's going to give me a lambda value. So I was going to do it ad hoc, but yes, that will make it much better. If you can't hear what he's saying, he cleverly said, because I have this constraint, we can set it equal to 4. So 4 equals, and then that will give me at least one lambda value, x plus root y. Okay, so I was on the right track to get this to the top, and then that is equal to what? Holy crap, lambda over 2 times 3. Let's get a common denominator. I'm going to sneeze again, frickin' Christ. Times 2 times 5. I'm trying not to sneeze is what's happening.
You're muted. Sneeze away, my friend. Let it out. Let it out.
It's going to go away. Just keep me rolling. I'll let you know if I'm going to sneeze. So I need a 5 over 5, and then a 3 over 3. And then so 1/2, I believe, works. No, wait. I did that wrong. Is that my favorite? Oh, 2 times 3 times 5 is 30. So then now what do we have? We have, let me erase that. Does that make sense to what I'm doing so far? This says 4 equals 8 lambda. I said lambda over 30. Now we got to multiply by 4.
120 divided by 8.
No way, don't. I was going to don't do it stupid like that. Lorenzo did it stupid. Let's do 1/2 times 30. No, wait. Yeah, 4 divided by 8, right, first. Then bring the 30 up. 15.
There's nothing wrong with 120 divided by...
Yes, there is. Why would you do 5 factorial? That's 5 factorial, not 6. We want 3 factorial. Okay. So that wasn't as bad as I thought it was going to be, but they're trying to lose you in that. Okay. So step 1, if you don't remember how to do it, go to the book. The other instructors won't admit that, but then we did find a constraint. Do I have to keep finishing the problem, or is that what we're doing? The lambda should be 15. There's only one value.
Like you said at the beginning, it's
So you just
doesn't
satisfy
exist.
one value, you're good. And you were right. The reason Lagrange doesn't work is gradients don't exist at 0.
Yeah.
I got another one from that exam if you want.
Okay, yeah, what do we got?
Total differentials. How to compute total differentials.
Total differentials.
In other words, this thing.
I don't know what you mean. You mean find.
That's verbatim. Find or compute the total differential for each of the 3 functions. And this is the definition of...
The total differential?
Yeah.
Wait, that's not as bad as I thought. They want the partial, right?
That's
they want
right,
the
partials,
partial
yeah.
of z with respect to x dx
That's
plus
it.
the partial of y. No, z y dy.
Right. Now we don't
So
have...
this is the one.
We don't have the...
What are they calling that? They're calling it the total.
differential.
Okay, because they're toning it back. That's the one form.
Yes. And they just want the general statement because we don't have any numbers to get deltas.
Is that a 3x to the y?
Yes, it is. Sign. Trig in a business class.
Okay,
Oh, my God.
I know. So first of all, that's why I was saying I didn't know what they meant by total differential because they're calling it that, but this is a one form because they're calling z equal to this. So I know it as, I've been doing too much stuff with Isha one, or that's that 315. But the first question I asked was, does he mean by total differential? He means this. And so that's the one form. And so now what we have to do is the partial of z with respect to x is the partial with respect to x of sine. Really, they're going to make me do that? Okay, that's not so bad. the second one might be a sine of 3x to the y. And normally if this was a function of x, that would be logarithmic differentiation, but they're trying to trick you because this I'm holding as a constant, so you can view it as an a or an exponent. So that's going to be, first of all, the derivative of the outside is cos of 3x to the y times, oh, and then the other one's going to be an exponential. I see what they're doing. And then that'll be times the derivative of the inside, which will be 3y x to the y minus 1. So that goes here. I'm not writing it out again. The partial of z with respect to y is going to be the partial of y of this guy, of sine of 3x to the y, which is going to be, again, cos of 3x to the y times the derivative of the inside. And now the derivative of the inside, you can think of this as a to the y is how your brain has to see it. So what's that going to be? What's the derivative of that in general? It's going to be times, so this is multiplying by this guy. It's going to be 3. We can ignore the 3. And then it's going to be x to the y times ln x log a. The derivative with respect to x of a to the x is a to the x ln a, which I always tell people in calculus. The instantaneous rate of change of all exponential functions is directly proportional to itself, and the proportionality constant involves the number e, because ln e is log base e of a. Anyways, there it is. This guy goes here. There's the total differential. I thought you were going to do total derivative. I was like, now we have to do, that's going to be the Jacobian, I believe, which would be the partial derivatives. What's the rate of change when you have more than one rate of change? But there, that's the total derivative. But they're making, it's hard to see. In the first one, I'm holding y as a constant, so it's just the exponential rule. In this one, they've reversed it, and I'm holding x as a constant, so then it's the derivative of the exponential function.
That was business calc?
Yes, this is second semester for Faculty of Business students.
Say that again. Say that again.
This is second semester calculus. Faculty of Business students have to do this. And what's new about this course is they've included a whole whack of probability questions based around, well, this continuous distribution. Continuous distribution integrals.
He doesn't have any more, unless you got one. Do you want to?
Now you can go to the plane now. Planes.
Once we're on the same page, yeah, that's the thing too, is when you bring me an arbitrary one from business, it's like, what are they calling things? The Lagrange multipliers, now I like that one. See, because Lagrange multipliers, there could be a whole bunch of cases, or they could be nice like us, and it just fell into the one, well, if you know the clever trick to adding those two equations. But it can get out of hand real fast, depending on which kind of functions they pick for you. It can be really nice or really mean. So then what we're going to do, plane 1 and plane 2. Don't worry, you don't have to do the calculus, Alessandra. What is this going to be? Oh, now I'm going to have to, okay, we're going to have fractions because I'm going to make it up. X plus y minus z plus 1 equals 0. I always pick that one. That's plane 1, say. And then what's plane 2? You want to throw some numbers out? I don't really care.
2x plus 3y equal, or plus 9.
Okay. There we go. That's not so bad. So what that's saying is, what we have here, what we've got here is failure to communicate. We've got a 2x3 linear system. I've got x, y, z, and now what they were doing is, the whole time they were catfishing you in week 1 of linear algebra. This is the question. What that's asking us, first of all, is can you find all points x, y, z in R3 that are on both of these planes? And it's going to have to be, if they intersect, if they're not parallel, they have to be in the same direction. How do I know they're not parallel? Because the normal vectors is this vector and then this vector, not the 9, but there's no z. and those are not in the same direction. If you want, we can check, but it's going to be a line of solutions, which means I should have infinitely many solutions. You can also, if you don't like this, you can put the information they didn't give us. If you want to make it a 3x3 linear system, just add the rows of zeros. But let's not do that, and then I'll point it out at the end again. Whew. Because what that says is, let's augment the matrix. 1, 1 minus 1 equals negative 1. And then 2, 3, 0 equals negative 9. Negative 9. All right. That's what I get for asking equals. So now what I have to do is I have a leading 1 for myself. So we're going to multiply by negative 2 and replace row 2 goes to row 2 minus 2 row 1. Now that'll get it a little bit smaller. It'll give us a negative 7. So that's going to give me 1, 1 minus 1 minus 1. And then 2 minus 2 is 0. That's why I did it. 3 minus 2 is 1. 0 minus 2 is 2. Negative 9 plus 2 is negative 7. That's not so bad. What does that say? That says that I am in REF 1, 1. That says that this is row echelon form. And then what that's going to say is X3 is free. And so in the first one we get X2 is equal to negative 2X3 minus 7. And then we're going to have to rearrange this. Which is going to say, whisper, whisper, whisper. I hear Ed Leonard in my voice again, in my head again. Stop whispering, you're distracting me. I can't think while you're whispering in the background. I like secrets. Yeah. What am I doing? What was I doing now? I forgot. Now I yelled and I can't remember what I was doing.
Is that the free variable there?
X3 is T. Just talking normally makes it better. I don't know why my brain, all I can hear is, my brain tries to think about what you're saying as I'm trying to do the problem. X2 is negative 7 minus, that's a 7, minus 2T. And then what's X1? That said X1 plus X, or I'm writing as X1, X2, X3, that's Z. That was Y. And then that says X plus Y minus Z is equal to negative 1. So this says X is equal to negative 1 minus Y plus Z. So X is equal to negative 1. No, that's a T. And that was Y. So negative 1 minus negative 2T minus 7 plus T. Is that right? Yeah. I hope so. I just erased it. This says X is... Negative 1 plus is 6 plus 3T. So that says X, Y, Z is equal to, or if you want the parametric equations of this line, is going to be X, Y, Z is equal to T negative 7 plus 2T and then 6 plus 3T. T is any real number. So that's the line of intersection. Because in the parametric form, the point would be 6, negative 7, 0. And the vector in the direction is going to be 3, 2, 1. 3, 2, 1. That was convenient. Holy crap.
How you doing there?
Ugh. I'm allergic to the chalk, I think. Possibly. Now what? You got another one from that horrible exam, or what are we doing?
Oh, I got one here for you. I got 2 of your algebra questions. This one isn't too bad. I'm writing up another one now.
I'm going to have to switch to frickin' the whiteboard one of these days.
Blue stuff. That's what I like.
The blue one?
Can
Can
you
you
see
see
One
the
will
blue?
make you sneeze too, but try this old blue.
Ugh. what does that say, 27?
Yes. So if you can verify that, that'd be great.
All right.
Or make it work out.
Push through.
We can switch to the whiteboard anytime.
After this one, we're switching to the whiteboard because I feel like I'm going to sneeze the whole freaking time. Look. It must be just the accumulation of it. I don't know. Ever since the table went up my ass, I don't have to write out A. What is this one? Easy. A and B are invertible. Do we have any more from the audience or no? Or are we just filling time? Because I had a couple from the I gotta find them now. I don't know where all my tabs went and I can't find them. I'm allergic to chalk, I think. That sucked. I like the chalkboard.
Unless you want to start wearing a dust mask.
No. COVID's over. COVID's over. COVID masks are like the left's MAGA hat. Okay, sorry. These are 4x4. Oh, I see what they're doing. No, wait. Okay, so what are they telling me? The determinant of b minus 1. Oh, they're taking the inverse of the inverse. A squared is 27. So that's the information they give me. And then they want to know what the determinant of 3. These are 4x4. That's important. 3 times a to the negative 2b transpose. Okay, the rules I want to use are the determinant of a times b is equal to the determinant of a times the determinant of b. The determinant of A inverse is equal to 1 over the determinant of A. And the determinant of B transpose is equal to the determinant of B. If you cofactor expand along the rows of this, you could cofactor expand along the columns of this guy. Oh my god, the blue didn't help. We're probably going to have to switch to the board soon.
Whenever you want to, we can pause for a second. We'll
Just wait, let me do this one. I'm already thinking. This one's 27. So, let's apply those 3 rules now. Oh, and what's the last one? Let's do it right here. The determinant of 3 times a number will be 3 to the 4 times the determinant of that other guy, a to the negative 2 b transpose. Now this will be 3 to the 4 times, wait a second, what? Oh, I see what they did. The invert, what are they doing to me? A minus 2, no wait. Yeah, I see what they're doing. B inverse A squared inverse is equal to A squared inverse times B inverse, which is equal to A to the negative 2 times B, which is equal to A to the negative 2B transpose if I'm going to do the inverse. So this is, what the hell are they doing? This is, did I do that right? This is, you're like the easy one. I'm going to fucking, Tim, you're not allowed to give me questions anymore. The hell's going on?
Well, you're on the right track. You just need a denominator of 3 cubed.
Yeah, I know. I'm getting there. I was just like, yeah, that is okay. That's going to be the one over the determinant of a, yeah, of a. No, it's backwards. How do I write this properly? This is the determinant of b to the minus 1 a squared, which is going to be 3.
That's right, because the denominator's 27 or 3 cubed.
It was this one, yeah. It was just this, yeah. I'm just joking this time. This one was just, yeah. They had to give me the, yeah.
So this is what my students at the University of Alberta are looking at coming up here on Tuesday, I think it is.
Yeah.
Here's another one from the same.
I said, what did I just say?
I couldn't get this to, this one buffaloed me. So, you know,
Buffalo, 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 buffalo.
buffalo, but not buffalo build. That would be bad. I can make some noise over here on the microphone while you guys transition to the other board if you want.
Yeah, I got to go wash my hands
Yeah,
and
go ahead and do
freaking,
that.
I don't know how I'm
If you
going to
would tackle
freaking.
that one, that'd be great. Although I think
All right, so we're gonna mute that
So
right.
my thoughts are that we might say transpose would be
You're muted. You're muted.
All right, he's muted. We're gonna take a quick break. We're not gonna cancel the stream.
Just gotta go wash my hands.
And I'm going to set up the camera. Tim's going to walk over here while he's setting that up and start talking to you while I change the camera. So enjoy this picture while Tim talks to you and I switch some cameras. All right, Tim, you got to come over here and talk.
Oh, this one's muted?
That's muted. You're
Alrighty. Yeah, the business of chalkboards, you know, is kind of interesting in that supposedly all the universities and all the schools got rid of chalkboards because of, chalk dust is bad, but I don't know any of the school marms that I went to school with over the years ever getting really sick from chalk dust. But then again, it could be also that, mind the way. Oh, you're good? Okay. Lorenzo's doing that producer thing while I'm just chatting on here, telling stories, because telling stories is what I do. That looks pretty good there, man. No, you had it. Now it's back. Okay, sorry. I'll tell the story. He'll do the alignments. Anyway, I like chalk, but chalk requires a degree of vacuum cleaning on a regular basis. I think we've just got too much accumulated chalk dust at the moment. So while Adrian's getting chalk dust off him a little bit, I'm just going to fill in here. Anyway, what we're looking at for this later in the week. So I know we have the linear algebra exam at the U of A coming up here real quick, and the statistics is also midweek, and again on the weekend. There's a lot of calculus exams on the weekend as well. I have the schedule here somewhere. So we're going to try to stream around this schedule as best we can. I mean, we can't do everything. We'll do it best we can. Like for instance, engineering, Math 102, linear algebra, that's towards the end of the exam period. We'll certainly have to hit that one pretty hard. Carbohydrate-based nutrition.
Give me that one. Yeah, these are the 4 food groups. That contains candy, corn, and sugar.
So that question is over there, wherever you put it.
I know I need this guy.
Oh, this thing, sorry. I didn't know what that little... He was doing sign language, and I didn't know what his signs were doing. So anyway, we have a bunch of stuff, subjects still to come. For instance, there's a bunch of calculus on the 18th, so we should do some review for that. And for people in the more advanced engineering classes, like I'm looking at Math 209, that's multivariable and vector calculus. That's a real beast of a course, and that's on the 22nd. So if you know anybody in those courses, you know, spread the word that we can do a review online for a lot of that stuff. How are we doing over here? We're getting set up. Looks like we're good to go. And let's put that schedule back over there.
Yeah, I thought you'd appreciate that.
I stepped in the damn water that the cat knocked over again upstairs. My socks are back.
So we're just getting the board ready, and then we'll get rid of this technical difficulties thing. Although I do like the, what's the news guy's name? I can't remember his name now.
Kent Brockman.
Kent Brockman, that's right. Boing. Hey, where'd the goodies go? I need some sugar.
All right.
Oh, we'll get
filling
there.
my face with Coke and I'm marking all up.
That's okay. I'll come mooch it. All right.
What is this problem?
Okay. You ready to go? Here,
Yeah,
take
yeah.
over, man.
I will take over the seat, and I will unmute Adrian. All right, Adrian, get out all your all your anger on the mic before I turn.
Do that.
All right, you're back on.
So anyway, my thoughts on that one are, if you do this, you're going to get zeros on the diagonal when you subtract, right? And you're going to end up with a symmetric matrix. So if you were to do the minor cofactor expansion, I think that will show that you have a non-invertible
Cat.
matrix. That's my thoughts. But I could be wrong. I'll leave you to figure that out. Yoink.
This was supposed to be an easy day. Why are you giving me all the hardest problems that you can think of? Stop that. Why does it have to be an odd integer?
That's a good question. Will is here to offer cat support.
Cat support? I don't know. Let's go back to doing the problems that I picked. Frick's sakes.
We can do that. All right, here you go.
Let's see. Let's fail at least one. I complained about them all, but I so far knocked everything out of the park.
Yes, you have.
So let's fail one, and then I'll switch to ones that I liked. So n is 2k plus 1. I don't think that matters, does it? Is that superfluous, or is it not? A is n by n. It's telling me. And then B is A transpose A. And then what do they want? B is not invertible. I don't know what the two ways are, though. It's saying hint, which doesn't help me at first. The determinant of B transpose. These are exam questions. These are like homework questions
Exam question.
that show that the determinant of B in two ways. Oh, I see it. I see it, maybe. Fucking home run. I wouldn't have got it without the hint, I don't think. But coincidentally, if you're still here and you haven't lost you, we're doing random questions from the University of Alberta and MacEwan, etc., and a bunch of these. So I didn't prepare any of those ahead of time, so I'm just trying to do them in real time. And you can see that you have to have some skill to be able to do some of these problems, and you should appreciate the fact that in my classes, this is what I'm saying, where I'm not trying to trick you or make you do horrible things. I just want to make sure that you can actually do basic determinants and eigenvalues and eigenvectors, etc. So why do we have to do it two ways? So B is not invertible. Well, I do know that the determinant of B transpose is equal to the determinant of B, which is equal to the determinant of... Oh, odd is important. I see it. I see it. Do you see it? Okay, I got it. Which is the determinant of A minus A transpose, okay? But now what is, that's one way. But now, oh no, wait, did I get it? Don't be excited until you get it. Oh, okay, and then B transpose is equal to A minus A transpose, which is equal to A transpose minus A transpose transpose. Clever. That's jerky. Okay, and then which was going to be what? A transpose minus A. But that's equal to what? Negative A minus A transpose. Do you see why it had to be odd? So that I get the power will say -1. So now if I do that, so just a second, now the determinant of B transpose is equal to the determinant of negative A minus A transpose, which is equal to, that negative has to come out to a negative 2k plus 1, the determinant of A minus A transpose, which is negative the determinant of A minus A transpose. And what's the only number? That's a number, remember. That's a number, right? So what's the only number that's going to do that? It has to be 0 because of this one. So what does that say? Did I do that right? Let's clean it up and logically do that. I don't need the information anymore. Somehow that's going to do it. So now what does that say? On one hand, we know, let's call the determinant of A minus A transpose equal to alpha. That might see it easier. Okay? So what we found on one hand was it's equal to alpha. The determinant of B transpose is equal to alpha. But then we computed it the other way and we got B transpose is equal to negative times the determinant of A minus A transpose, which is negative alpha. So how can that be? The only way, what's the only number that's equal to its negative? Alpha equals 0. So because of that, that says that the determinant of B transpose is equal to 0, which means B transpose. Oh, and then it was show that B is not invertible, right?
That's right. You got the right answer.
Yeah. So then show that the determinant of B, which is equal to the determinant of B transpose, is equal to 0. And that's if and only if B minus 1 does not exist. Pen drop. I don't want to ruin the pen though. Okay. The one good thing about when you give me problems I can't do. Okay, what do we got in here?
Do you want to finish that thought? Because I'm curious now.
A what? What thought?
The one good thing about giving you problems that you don't know how to do right
Oh,
away.
time flies. I'm like, we're already an hour and a half in. Holy crap.
An hour and a half into yours.
Well,
We're
and then the
2.5.
second thing is it shows that I frickin' do know what I'm talking about, and they should hire me at MacEwan, but they're gonna get rid of me instead. Oh, I shouldn't have said that one. That was the second thought.
Well, let's put it this way. You can't fake having a PhD in mathematics, right?
No, I've done a few math problems before.
Yeah.
Fake it till you make it.
That's
Are
right.
you gonna put that one back?
I'm going to put this one back. I don't have any more.
Now I want to do another Lagrange. You don't have another one for me?
I'll get you.
No.
That
To
would be
to
nice.
end off, we're gonna do the problem that the kid posed for me.
Oh, okay. Which one?
The arc length. I'll show you. Let's do it right now.
All right.
Zoop, zoop, zoop.
We also have a question here too.
Okay.
Take a peek at that one. This one's unrelated to other things though. So if you want to get to the actual questions first. While he's processing,
What
we'd
the
like
heck
to
does that say? I don't know what that says.
the thing to prove that if A naught less than A1 less than AN, then the
I don't know what this note.
Increasing sequence. No,
no, that's just
that's increasing.
that. Yeah, it's
That'd
an
be A
increase.
sub 1, A sub n.
Yeah.
So this is a sequence question.
Then the family of polynomials.
Oh, that confused me. Okay, wait, what?
So A sub 0.
I said no more new questions. I'm doing my question. Can you write it out in plain English and then give it to me, I guess? I don't understand. What? Did any of these pens work? This is what you're saying?
Yeah, that's what he's saying. So if that, then the family of polynomials x plus a sub I
I need pens that work just a second.
to the power of n.
Does this one have juice in it? Okay, that one has some juice in it. Just a second. This, you're saying?
And I is between 0 and n.
Yeah, for these guys.
Is linearly independent. So the family of polynomials is linearly independent.
Okay, so when I make that the old man noise, it's because I have a sore rib. It's never going to go away, I don't think. So my constraint is these are all strictly not equal to each other. So they're all strictly less, they're not equal to each other, right?
That's my interpretation as well. Yeah.
And then what's the family of this? So I have x I don't want to FOIL that out. So and then I have to use the binomial theorem. Really?
Looks like it, yeah.
This is going to be non-trivial, but then what that says is this is x plus a 0 to the n, comma, x plus... The first thing you want to do is don't write it as the family or write these vague words because it's like trivially true that means this is what it gets. So this is what they're saying, x1 to the n times x plus a n to the n is linearly independent. But what do they mean by that? What do they mean by that is, okay, crap. What's the binomial theorem? I better remember what it is. So x plus a, I'm going to use a k, I believe. What did you use? You use an I. Just a second. So x plus a j, I'm going to use that because that's my name, to the n is equal to what? The sum from I equals 0 to n of n choose I. Let's make this x to the I, a to the n minus I. Okay? Which means you could write all those out if you want. What that means is if I write that out now, what is that going to be? If I put I equals 0, that's going to give me 1 times... maybe I should switch this so that it's a monic polynomial. N minus I. It doesn't matter which one you pick first. Okay? Do you believe me? So then that's going to give me 1 times x to the n. It's not monic, but it has this. You can divide by this guy. If these guys are these guys positive, it didn't tell me that. Times, that should also be, and that's the j. Sorry, that's the j. I forgot the j. Then that's going to give me it does give me monic because that's 8j to the 0 plus n choose 2 times, I'm just showing you what it looks like, n minus 1. A j to the 1 plus all the way down to what's the last term I put in there, n choose n is also 1 times n minus 1 will give me the constant term, and that gives me a j. So that's what each one looks like for j equals 1 to n, for j equals 1 to n.
In your n choose 2, in your second term, would that be a 1 or a 2 there?
Don't correct me, but you're right.
I question, not correct.
No, you did both. That's just my joke every time. Good. You can write all those out horribly, but now I just want to do that because what I want to do is anytime they give you this abstract thing, I want to do now this. That is a polynomial in n plus 1. I can start it up. So what I'm saying is, instead of viewing these as polynomials, each one of these is going to be, so this one now, I'm going to put 0 in there for the j. So this vector is the vector 1, n choose 1 times a0, n choose 2 times a0 squared. That looks like dot, dot, dot times a0. That's the first vector. This polynomial is the vector in Rn plus 1. And then I want to show that now the last vector is going to be, oh crap, now I have to do this. This is going to be also a 1. And then this will be n choose 1 times an. That should be to the n now, shouldn't it be? Yeah. Yeah. N goes down as you go on the powers of x, and the a0 should go up, right? Yeah. I'm talking to myself. Is anyone else following what I'm doing here? A n to the power n. That looks like the Vandermonde, sort of. Now, if I do that, I would want to ask equals 0, equals 0, equals 0. So that would be the augmented matrix. I don't know. I've never seen it before. Why is everyone giving me the worst problems in the world today? Stop that. And now you can say that, what am I trying to do? This should be to the power n. How come you get a unique solution? I don't see how I would want to do this. Now you just want to show that I don't want to do it anymore, but now you can just show that when I row reduce this, what's the hot mess that I'm going to get? I think it's that you want to get to you want to get to REF in this form. Right, because I can kill all of these ones. And that's going to give me some hot nightmare mess, because this is all ones in the top row. So I have a leading 1, and now I want to kill below. But now to kill below, I have to multiply by all those n chooses. So what is that going to do for me? That's going to give me gross. So this way, 1, n choose 1, a0, n choose 2, a0 squared. No, that should be a1 now. a1 to the n. Is this positive? No. Is that the answer? Do you know that these are non-zero or non-negative?
We don't know that. Or at least it's not stated.
Well, I know, especially on the internet. It's like, is that the actual question, or is there a piece of information missing?
Not necessarily positive. Okay.
But they're just strictly decreasing. I know the difference of any of them are not equal, right? Oh, I see why. So then, okay, I'm not doing it anymore, but okay. What you can do is you can kill, to go from that to the Brown matrix. What you want to do is the top row is not going to change, right? 1, 1, all the way to 1s. But now what I'm doing is, in each of these ones, I'll do the first move to show you what I'm going to do. To get rid of this one, I have to multiply by negative n choose 1 times a0 to get rid of that, right? But then I'm multiplying that into all of these rows. But do you see that's going to give me, okay, maybe I can do, as I start doing it, it starts to fall out of what I'm trying to say here. This is going to give me n choose 1 squared, whatever that number is. I don't really care. But then what is that going to give me? A1 minus A0, which is not 0, is the key here in each one. Do you see it now? That's going to give me n choose 1 squared minus an minus a0, which is also not 0. So I can divide by that to get a leading one in the next one. So then that's going to give me zeros, do you see, all the way along. And then, yeah. And then divide by this, which is not 0, and you'll get, in your RAF, you'll get 1s all the way down, which means they're linearly independent. Look, I'll leave you. I don't remember. Does that make sense, though? Or do you want me to finish off the argument? Do you see? Okay. What I did was I turned it into vectors. Let me do this. Does this make sense? Before I switch, I'll tell you, you're asking me. So any of these n chooses is not 0, and now because these are all strictly less, any one of these, the ai does not equal aj for any I not equal to j. Because they're all strictly less, this is a strictly increasing sequence or function, and functions that are monotonically increasing by definition have to be 1-to-1 because they can't have this, they're increasing, so they can't have the same value ever. So the difference of all of these, right? This one, I can say, it doesn't matter which one you subtract, but if you subtract from both sides, that says 0 is strictly larger than a1 minus a0. So they're all going to be positive now, any of those values, even if they weren't negative necessarily. Now when I do that, each one of these is going to be not 0.
That's every step. That's not just the first one, right?
Right? Yeah. So then what? So yeah, that's why I'm running out of board space and that. But if we do that one more time, what that says is now I'm just going to run my mantra. I have a 1 here, and then I have zeros all the way down. And then now I know this is not 0. So I can divide by that to get a leading 1. And then now that's going to be, each spot is going to have, that'll actually cancel off. The choose 1 squared will cancel with that guy, and then that'll be a a1 minus a0. Do you see all the way down? This will be, what was that? This is the 1 spot. So this will be a2 minus a0 over a1 minus a0. Right? And then I kill below. And then I move to this, and then I can divide by that. But any one of those is not going to be 0 because all of these are not 0 because A2 is larger than that A0 also. And then eventually you're going to get to an REF that has 1s all the way down and then 0s below. And then because of that, you have a unique solution, which means you have the unique trivial solution, which means they're linearly independent. But I think now what you're asking was, how do I know that the polynomials are identified with those vectors? Pn is isomorphic to Rn plus 1. Any polynomial, so let's just do P2 is isomorphic to 2, which is R3. Just so you can see this, let's tone it back. Any ax squared plus bx plus c can be just written as the vector A, B, C. That's what I did. Any finite dimensional vector space can be written as a copy of Rn for some n. 2 by 2 matrix, these are 4-dimensional. Because I just write it as the vector A, B, C, D. So when we're doing finite dimensional operators, we can view it as just linear transformations on Rn to Rm. I'm still going to sneeze from the whiteboard, but or from the chalkboard. So what I did was, the first thing was, when they give you some abstract nonsense, in my mind, because I have a PhD, as soon as they do this to me and they talk about linear independence, I'm going to turn them into vectors because it's much easier to see the linear independence of the vectors this way. Therefore, those polynomials are all linearly independent also. Good. Save that one, I guess. Thank you.
Yeah, great question. That was good. That was good.
Now I have no idea what I was going to do now. Oh, yes, I do. The
All right, so we'll end on this last question then that you're just about to do.
Yeah. So, which looks like a horrible nightmare. Let's see how far I get. So he's making a video game where you have a grappling hook. So he has his little square, and then he hooks onto here, but then he can swing around and do stuff like this. Is what the video game's doing. And so what he was asking, where did I just put that? I need that. So what he's asking me is, at every point when you're not fully extended, so this would be the length L. So let's do this first of all. Let's recap what I did. Let's call this AB. Let's call this CD. Let's call this EF, points in the plane. So first of all, what's the length of L? By Pythagoras' theorem, L is equal to the square root of E minus A squared plus F minus B squared. Okay? Then what he wanted was, he wanted to know, he wants it in his thing, he didn't know how to code that there's got to be a parabola through this. So if I use all 3 points, I could actually get the Vandermonde matrix. But now for convenience sake, what I'm going to do is I'm going to call P of X equal to, instead of ABC, because I've used ABCs again, and I want to turn this into a linear algebra equation. I'm going to call this x1 x squared plus x2 x plus x3. And then how do I get the Vandermonde out of that? I know that this parabola, or this quadratic equation, is through these 2 points. So I have 2 pieces of information. So if I do P of A, that's going to give me a squared x1 plus ax plus 2 plus x3 equals b. If I do that through this point, I'm going to get P of C is equal to c squared x1 plus cx2 plus x3 equals d. Now what do? I augment the matrix, and then you see if I put the last equation in there, I could get P of E is equal to e squared x1 plus ex2 plus x3 equals f, and that's the Vandermonde matrix. Do you see it? A squared, C squared, E squared, A, C, E, 1, 1, 1 equals B, D, F. Except he doesn't have that last equation. We don't have the last one. So this is the system that I have. So there's a family of these. Now again, what am I doing? I'm phrasing this as I'm looking for x1, x2, x3, the unknowns of this quadratic or this parabola through those 2 points. So now what can I do? I know that because it's a quadratic, and that I'm assuming, without loss of generality, that you didn't put this at the origin. So I'm assuming A is not 0 and C is not 0. So also, again, why can I do this? So what that says is I can write this as 1 over A squared, B over A squared equals C squared, C1D. Then, again, things look different, but I'm now solving a linear system. I get a leading 1 in the top left corner, just like I did with the other ones, to show that they were linearly independent. And now I'm going to multiply by negative C. That's going to give me 1 over A squared, B over A squared. You can all put this into the computer once you find it, and then you can simplify, and that will give me C squared. C minus C squared is 0, and then what are we going to get? We're going to get C minus C squared over A, and then 1 minus C squared over A squared equals D minus B times C squared over A squared, close bracket. Now this is already REF, and then so you can solve from that and find that x3 is free. You're going to find a family of parabolas, and then you can solve for x1 and x2 in terms of that. So that's the problem that he wanted me to do. They looked better when I didn't run out of room, etc. on the board. But then if you wanted the last constraint, can you see what it would be? The nightmare? Yeah. Let's do that. Let's start that. I'll show you. I can get through pretty far. So let's try to do this. So what is the length of the arc between A, D, and CB? My parabola was x1 x squared plus x2 x plus x3 between A and this. So it's going to be the integral from A to C of what? The square root of 1 plus dy dx squared dx. This is y. So let's do that. dy dx. This turns into a nightmare. I remember doing this. It took me about 3 pages. I don't know where they are. I think I gave it to the student.
This is cooking with calculus now.
Yeah. So this is 2x1 plus x2. This squared is going to be this squared, which is going to give me what? A headache, among other things. This is this squared, so let's multiply it by itself, which is going to give me 4x1 squared plus 4x1 x2 plus x2 squared. Now add 1, right? Which is going to equal 4x1 squared plus 4x1 x2 plus x2 squared plus 1. I just wrote that out again. But what I want to do is this. This is, I'm definitely allergic to chalk, I think. Let's take this 4 out. This is 4x1 squared plus x1 x2 plus x2 squared plus 1. Wait, I did something wrong. Dip. You see what I missed? Let's try that again. It's the x1s and the x2s. I'll stick to what I did originally. dy dx is equal to 2x1x plus x2. There we go. I was missing the x. I'm like, where'd the x go? This squared is going to be this times this, 2x1x plus x2. I'm like, I was about to complete the square, and I'm like, where's the x for the completion of squares? Which is going to be what? 4x1 squared x squared plus 4x1 x2 x plus x2 squared. That's better. Plus 1 will give me this, plus 1. Don't worry, I got all the way to the secant value, and then it's secant cubed. When you do a parabola, it's secant cubed, which is the, what is it? Secant theta tan theta, 1/2 secant theta tan theta times 1/2 times the natural log of the absolute value of secant plus tan theta. Just a second. This is equal to, now I can complete the square. So what do I have? I can take 4x1. Let's get on my knees for this. Please, God, help me. This is this is going to be 4. This is x squared. Now the mantra of completion of squares is get this to be monic, which is going to be what? I can take that out, or it's going to be 2 over x1 times x plus, I don't care about this guy. It's going to cancel off anyways nicely, which I found out accidentally, which is going to be what? 4x1 squared times, now what do? I can complete the square. So b over 2 is 2x over x1 squared. Squared is going to be x2 plus x2 x1 squared plus x2 squared over 4x1 squared minus x2 squared over 4x1 squared plus x2 squared plus 1. Let's move that up. I'll do it. I've done this before. That's disgusting. You want real numbers in there is what you want. So now what is this equal to? This is equal to 4. Wait, it gets worse. I think I made a mistake last time too, so I think I found my error. This is 4x1 squared times, now this is the completed square on the inside. No, we did that right. Oh, it does cancel off nicely. Do you see it? Ha, this is good. Shush. I asked for comments and then shut up immediately. I'm on a roll here. This is what? Plus x2 over 2x1 all squared. But now make sure you redistribute that, do you see, onto that guy, which is, these are going to cancel, plus 1. That's on the inside still. Wait, Let's not be smarty pants. Yeah. That's that guy plus 1, right?
He's not just talking to himself. I've unmuted the mic. And
Okay, yeah. Now be quiet. Let's make sure we didn't make a mistake, though. Did we not? I completed the square. That's this guy on the inside times that. And then I distribute that, and those cancel again, and that gives me then the negative x1 squared, and the x1 squared cancel plus 1. So now, what do we have to do? It's the integral from a to c. It got actually better because last time I think I forgot something. Well, we'll see in a second. We'll see. Do you see what we have to do now? That's the square root of x plus x2 over 2x1. What are you doing there? Squared plus 1. Yeah, I did something. That was even better. That's not so bad.
Where did the 4x?
Yeah. Just wait. Right there. I took it out, square root. Oh, I see. Okay, yeah. No, that's where it went. That's where it went. Ha ha ha. So let's multiply by 4x1 squared over. I was like, there was a horrible 4. There was a something else there. Let's multiply by 1. Now I'm going to square root it. Now I can take it out, but then what do I get? Oh, there it is. This is 2x1 times the square root of x plus 2x. I did it when you're don't have an audience, it makes it better, and that's going to be what? 2x1 all squared dx. So now what do I have to do? Substitution. W is equal to x plus x2 plus, this is a shift or a baby substitution. I say it's not so baby when you don't know what the numbers are. dw is equal to dx, but now this is x equals a and x equals c, so that means w is going to turn into a plus x2 minus 2 over x1 to w equals c plus x2 plus 2 over x1. So then this integral is going to be integral of 2x1, the integral of a plus x2 over 2x1 to c plus x2, I said, 2 over 2x1 of the square root of w squared plus 1 over 2x1 squared dw. Now what? Trigonometric substitution, that's correct. Now I'm going to let I'm going to let w equal 1 over 2x1 tan theta. Then dw is going to be 1 over 2x1 secant squared theta d theta. And the square root of that thing, blah, 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 is going to be equal to 1 over 2x1 secant theta. See the secant cubed show up? And then also, what do I have to do? Change those bounds, but I'm not doing that. So here's how you do that when that's a hot mess. We're now going to just look at the integral. We're going to turn it back into the x's, and we're going to do this. So I'm going to ignore these. So now I'm looking at 2x1, the integral of w squared plus 1 over 2x1 squared dw is equal to by my trigonometric substitution. This is equal to 2x1, the integral of 1 over 2x1. Those ones are going to cancel, times secant theta, and then I have 1 over 2x1 secant squared theta d theta. Squiggity. That made me feel happy a little bit. So does this integral. So this is going to be 1 over 2x1 times the integral of secant cubed theta d theta. If you don't have this memorized, we're going to use integration by parts, so you should actually leave it like this. What can I integrate this tan theta? What can I differentiate that guy? But when you do that, you're going to get 1 over 2x1 times 1/2 secant theta tan theta plus, let's make the 1/2 go on the outside, 4 times the natural log of the absolute value of secant theta plus tan theta. This is not my first rodeo. So then we're going to get that. How do I turn back from that? Oh, I need the c's. I know what the bounds are. And I was like, maybe just pick an arbitrary parabola, because this is what you can put it in the computer. It won't be so bad. The computer will do it fast. Now, what do I have to do? Well, I have to do this. Theta's here, and what did it say? tan theta was equal to 1 over 2x1w. Is that right? No. 1 over 2x1w is equal to that. So tan theta is equal to 2x1w over 1. Tan theta is opposite 2x1w over 1. So that means that this is the square root of 1 plus 4x1 squared w squared. So you have to put that back in there. Holy crap. Blah, 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 blah. Now you can see that I'm almost done. I don't want to do this computation anymore. I already did it once. So secant theta is what? Cos theta is adjacent over this. So secant theta is this guy. Did I make a mistake somewhere? No. This is secant theta is the square root of 1 plus 4x1 squared w squared times tan theta, which is 2x1w, plus the natural log of the square root of 1 plus 4x1 squared w squared plus 2x1w. I ran out of board. And then what was that? That was evaluated from those two bounds, which was, the bound was a plus x2 over 2x1 to c over plus x2 over 2x1. Easy, there's the arc length. That's all I'm doing. But yeah, do you see the hot mess? I'm like, maybe you don't want to know the arc length. Just pick one of the arbitrary values. So the last question you get was, when you did that, you let the x3, we had x1 x squared plus x2 x plus x. You already forgot what we were doing. But I'm doing the last constraint. And then this integral would have to equal the L, remember, from the arc length. That's what you want. You want the arc length of that parabola. Where's my erasy boy? My erasy boy, I just called it. Where's my erasy boy? Now I don't need that anymore. Ooh, I knocked stuff off the shelf. My butt still hurts from that frickin' table. God damn. Right there. Can I show everybody? It's like, yeah, you're showing. Yeah. You angled it down a little bit more. 3.1415 you need it on there. It does say pi over there somewhere. What was I doing? This. Before I started to scratch my butt online. We wanted the parabola through that had the length L. So that thing that I just calculated has to equal the length L of the total rope. But.
All right.
This is how you do real world problems. It was an interesting problem. Time out.
No, I just wanted to chip in case we still have anybody hanging around from that linear algebra question that was about A minus A transpose.
Okay, yeah.
That, when n is odd, that produces a skew matrix. According to Jacobi's theorem, the determinant is always 0.
Oh, so I did it differently. See,
No, but you did it fine. But the point I'm getting at is you just rediscovered something.
I think I'm just proving what Jacobi's saying.
Yes. But the thing is, they're hitting first semester linear algebra students with that question.
But also, don't try to use a big Jacobi theorem because you can't see it. Try to do it brute force first. Yeah. And this is also why I'm usually good at math, because I'm not a smarty pants. Yeah. I'm a brute force type of guy. And using fancy techniques when the student is never going to use the fancy technique is not very good.
Most importantly, you like cats.
I like cats and math.
There we go.
Can we? Cats. I know. I was like, it's that one. It's that one.
I'm muting Adrian now. Thank you, everybody. Adrian's going to show some cats or some trinkets or some stuff. He was taking off his microphone, so I thought, okay, we might as well mute it. And so thank you, everyone, for joining us. I'm going to post a link to Patreon now if you would like to consider supporting us. And we will be back tomorrow, right, guys?
Yeah.
You bet.
Excellent. Tomorrow, same-ish time, same cat time, same cat channel. Thank you, everyone. More practice problems tomorrow. Goodbye.